It's good.
Let's ask. Should we wear this?
We wear these while we're talking?
It's not necessary.
Not necessary. Okay.
It's for all the listener people.
Okay.
Let me make sure it's being recorded. Okay, perfect.
Hey, how's it going?
How you doing? You guys good? You guys good?
Yeah.
Oh, yeah.
Go.
Hey, how you doing?
Good to see you.
See you.
Awesome.
Okay. Go get
Hey,
it.
good to see you,
Excited
Kevin.
for this. Good to see you.
Yeah. Right.
You want to start?
Yeah, sure. All right. Can everyone hear me okay? Yes? All good? Great. I think we can get started. So we got a lot of material. We're going to tell you how to build models from scratch using open source software. And let's see, we got a lot of really exciting topics to go over. We're going to see, starting from a foundation of models that are built by the transformer inventor, Ashish Vaswani. He'll join us in a little bit, but we're going to lay the groundwork to start with of what are we working on, why are we working on this, what are some of the open source pieces that we used, and why did we build them, what is the architecture. It should really be hands-on, so you should really have an idea after this how to build your own models, how to feel confident about using open source software to create something completely from scratch. And we're not going to do it at small scale. We're going to do it really at very large scale. So it's not going to be Claude 4.6 scale, but we're going to do post-training. So it's about as big as you can get without being a frontier lab. So before we get started in the material, I think it's helpful if everyone can join the Wi-Fi. Also,
do we need to introduce ourselves?
I usually will, but
You just okay. I don't know. Go ahead.
the beginning is the introduction.
That's true.
Yeah. Okay, I guess I'm going to leave this up for a few minutes, just to give everyone a chance to log in. Okay, but yeah, I think that's a good idea, Farbod. Let's do like a really quick intro, and then we can do a little bit more in-depth intro as we go through. But hey, do you want to get started?
No, you go ahead.
Okay, I'm Greg. I'm the ScalarLM Architect. We're going to run on TensorWave, and a lot of this work has been supported by Relational.ai. So just want to give those shout-outs. Farbod?
I'm Farbod, data scientist with AT&T.
Awesome. Okay. I'll talk a little bit more about how we got here, but I really just want to leave this up for a minute or two, just to make sure everyone has a chance to get the Wi-Fi. I guess the idea is we don't want interference between the different arenas.
Do you want a chair or no?
Sorry?
You want a chair or no?
I like standing, but I'll sit eventually. Okay, I also kind of want to make this interactive, so if at any point, there are going to be two sections of this. The first half we're going to talk about what we did, what the open source software pieces are, and then in the second part it's going to be very interactive, and we're going to have a live demo of like what is the experience of actually training a model. You get to see some models be trained. Anywhere in here, I'd love to understand questions, the topics that are really on your mind when you're thinking about building your own models. So I think there's mics. We got at least one mic. I think everyone's got headphones. You should be able to hear. Just maybe like raise your hand, like a big raise hand somewhere in here. We'll also have some points in the middle where it's kind of a little bit cleaner and easier to do questions, especially in the live session. But yeah, we're going to have plenty of time. So I'd really like to make sure we can respond to questions, and there really is an enormous amount of material. I think this session is scheduled for 3 hours, but usually when we do this, it takes about 30 hours.
Yes.
So, there's plenty of material that we're not going to cover, but if there's something you're curious about, just ask us and we can switch and we can cover it. Okay, I think this has been up long enough. I feel like it's a good time to get started.
Perfect.
Everyone okay? Everyone's got it down? All right.
Oh, it's
Here,
with this.
I pressed on the wrong keyboard. Okay, so I'm going to talk a little bit about some of the pieces that went into the open source software stack that we're using here. We're building open telco models, and we're building it with a software framework that's called ScalarLM. So I think of ScalarLM as an 8th generation training and inference technology, and this is a little bit of the background of how we got to ScalarLM. So back in the day, this was about, if it's 2026, this was 2013 or 2012. I was working at NVIDIA, and I was the software architect for this, which is CUDA. So we were trying to figure out how to make GPUs programmable, and GPUs were massively parallel, had tons of cores. They were really difficult to program. We tried all sorts of things. Almost nothing worked. The only thing that ever worked was this thing, which is the first deep learning training computer. I built this with one other NVIDIA engineer with the Stanford AI lab, which was Andrew Ng's lab that was originally in Google Brain. And then this was the scaled up version of it, which was done in Baidu, the Chinese search engine. And we figured out how to train neural networks on machines of this scale. And this was, multiple thousand GPU scale. So in order to do that, we had to solve all sorts of problems. One of the problems was, how do you split up the neural net over all of the different machines and all of the threads and all of the cores, the millions of threads and cores in that huge machine? How do you take one problem and get all of those resources to all work together to solve the problem? So we invented collectives. We'll talk about this here. We're going to reuse these here. These eventually became part of collective libraries like Nickel on NVIDIA or RICL on AMD. Some of the other things that are going to be foundational technologies that we're going to use here, mixed precision training. So we realized that it's possible to shrink the numerical representation of the weights of the neural network. And by doing that, you get a massive increase in efficiency. And it makes it much easier to run in parallel. So this is work that we did around 2016, but we published it in 2018 when NVIDIA released what's called the Tensor Core, which is the hardware acceleration for these formats that we discovered. And there are all sorts of things that happened from a research perspective 10 years ago. I'm going to mention this one too. So this is probably the most useful one. So this is now called language model scaling laws. So in Baidu, we wrote the first paper on language model scaling laws. This is our scaling law out of our figure from 2017. This thing is the premise of machine learning. This is the premise of language models, of large language models. Back then, we did these experiments on a small language model. It was a model with 50 million parameters. 80 million was a really big run. But scaling laws are a straight shot to large language models. You follow the line, and it leads to large language models. So, and this is just a little bit of a retrospective on scaling laws. This is from the former chief scientist of OpenAI, Ilya Nurup's keynote. So he called scaling laws the driver of all progress in AI in the last decade. So this is what gave us language models that we're using today. So we're gonna reuse that. We're gonna reuse the scaling law concept. But the premise of it is that you need an enormous amount of compute, and as you invest an enormous amount of compute in training one of these models, it gets smarter. And eventually it starts to learn new abilities. And if you feed it data with new skills in it, so here we're gonna look at very specific telco oriented skills, like how to do root cause analysis, how to generate embeddings that actually understand technical content. We see that the models get better. They get better at the things that they're already good at, and they learn new abilities. So back then, we used these models. I like to joke for the input method, which is like if you've ever swiped on your phone or typed into your phone and it auto-completes the text. that was the original application of language models. Those are the language models we had in the early days of scaling laws. But now they can solve complex technical problems. They can write code. They can write software. They can write complete production code. They can do many different high intelligence tasks. And the expectations of scaling laws is that it's just going to keep getting better. This is why people keep investing larger machines and more energy into training these things. So, let's see. So if we fast forward to 2026, this is where we are today. This is a figure from a pretty good open model, which is Qwen 3.5. It came out last week. The best models use reinforcement learning. So this is just showing the progression of a really good, near frontier level language model as they're adding more reinforcement learning training environments. We'll talk a little bit about what that is. The reason I'm mentioning this rather than Claude or OpenAI is because this stuff, they at least publish the model and they publish some of the training methodology so we can see what they're doing. So this is their figure from their blog about what their infrastructure looks like. What did they need to do to train using reinforcement learning this frontier level model last week? There's really two things in here. And we've kind of moved on from pre-training. So in the days of pre-training, we used to just predict the next token for a huge amount of data on an enormous GPU cluster. Evolutions of the one I showed in Baidu. But today, we're also doing inference. So the models are thinking, and they're planning what should happen next, and they're learning from that, what works and what doesn't work. And then the learnings are baked back into the model, which is still using training and still using the same backpropagation, the same distributed training technology that we've been doing for the history of language models, or deep learning language models. So if you really want to do something like this today, you need infrastructure that can do both of these things. It's not just training. You also have to be able to do rollouts. You have to be able to do inference. And you have to have it all integrated together into a single system so you can build a single model. There's no way if you did this as a one-off, you'd be able to do it for 17,000 different reinforcement learning environments. You need a high level of automation to be able to do something like this. So this is why we built ScalarLM. Okay? ScalarLM I think of as the 8th generation. The first generation was the version we wrote for that Baidu cluster about 12 years ago. And over again, we kept incorporating new improvements into it. And it hasn't always been open source. The first version of it in Baidu was actually called Majel, and it was closed source, and it was used in a bunch of Baidu production systems. A bunch of these things have been spun out and better optimized, and the open source community has made a ton of progress on it. So we're kind of including back the open source pieces that have made a lot of progress. We're wrapping it all up, and then we're filling in all the gaps. And I think the biggest gaps that we've seen are around joining training and inference together. There's pretty good training frameworks and pretty good inference frameworks, but they're usually not joined together. So this is really a joint effort. We'll talk about contributions. Relational AI has built a lot of software to help this out. TensorWave has built enormous GPU clusters that we'll talk about, and we'll show you an example of training on one of them. AT&T, Farbod, especially, has really brought it all together and built real applications on top of that. And as part of Open Telco, how many models is it?
30.
We got 30 models trained on this that are all open source, open weights, the entire data set, entire training stack, all the weights are open source. And it's a starting point and they're raw ingredients that you can use to continue building with. So one of the most important things about being open source is that it lets us be hardware agnostic. So ScalarLM runs on NVIDIA GPUs because there's so many NVIDIA GPUs. Really, after Tensor Cores came out, they took over the world. They're everywhere. So we run the workloads that are already running on the infrastructure that's already, there's a ton of NVIDIA infrastructure. but we also have the ability to move it all over to AMD. We don't support everything. It takes a lot of work to support different accelerators, but this stack that we're going to talk about runs both on NVIDIA and AMD, and it's pretty easy to switch back and forth between them. And it's also pretty high level. This is just an example of maybe 20 lines of code where you can write one of those complete reinforcement learning loops. I would say there's a bunch of frameworks that let you do this, but very few frameworks let you do it this simply at this scale. Once you start getting more than one GPU, when you start getting hundreds of GPUs involved in this, it gets really tricky. As we'll see, it's not going to be, you'll see a lot of the what goes on under the hood today. But if you get all that stuff all worked out, you can write code that's like this, that's actually very simple to post-train models. Okay, so this is just a look at how ScalarLM fits into the ecosystem. Biggest things, it's both inference and training glued together. Some other things have inference and training glued together. Most, probably easily, is just Hugging Face. If you just Hugging Face, download a model, take a few training steps, call a pipeline on it, it's pretty easy to do that. It's harder to do it as you do it at scale. There's a lot more involved as you do it at scale. So we'll talk about that. Also GPU agnostic. It's really hard to kind of get the same stack that's going to run on all the GPUs that are available. And there's many stacks that work on NVIDIA in particular, like Megatron is a pretty good pre-training stack that works on NVIDIA. But migrating Megatron over to AMD is quite a lot of work. Other things like DeepSpeed historically have been able to do this, but it's tough. There's a lot of work that goes into these things. And then there's a bunch of like single GPU, single node frameworks that can do post-training, but they can't do at scale. And they typically don't integrate inference. Some of them do. But I think of ScalarLM, I wouldn't really think of it as like we're trying to be a new project or something, or like a lot of new code. It's really just trying to package up all of the stuff that's best of class, that's open source, just all in one place, so that it's easy to build applications on top of it. Okay, so I'm going to spend maybe 10 minutes on just telling you how ScalarLM works a little bit under the covers. So this is the high-level block diagram of what ScalarLM is. It's really gluing VLLM together with Megatron and Hugging Face. So most of the code is going to be just whatever was in VLLM, and if you understand VLLM, you probably understand how to do inference in ScalarLM. If you understand how to do training in Megatron or to use Hugging Face models, you probably understand how to train models in ScalarLM. And then the thing that's tough about this is it's really scale and gluing them together. Normally, they're separate pieces of software. If you try to, actually, I'm kind of curious. How many people have like deployed models? Have you ever tried like training your own model and then like deploying it, on an inference stack? Yeah, a couple people. Okay, so I'm just going to say what the experience is if you've never done this. It's usually you train the model and then you get some weights out of it, and then you have to figure out like what is the production deployment cycle of your model. So you have to maybe convert it between formats, you have to move it over to inference servers, you have to like redeploy. It's sometimes multiple engineers to do this, depends on your organization, and almost always it's time. It's not something that happens instantly. It's something that's measured in like actions, and I've seen deployments take multiple days or weeks. So that doesn't really work when you're building reinforcement learning frameworks where individual training steps need to publish new models and incorporate the updates from inference on those new models. So gluing them together is, through here, we pass the models from Megatron into VLLM automatically. That's one of the hard parts. And then the other hard part is at scale. And it's both at scale for training and at scale for inference. How do you keep 500 GPUs busy? How do you schedule, appropriately on all of those GPUs? So we're going to talk about how does that work. We mostly, I would say, try and reuse existing technology, like we reuse Slurm. The way inference is done, we had to rethink it a little bit because inference today is kind of designed for, I'm going to say, chat. It's designed for, it's designed for ChatGPT, but that's not the right way to do it for RL. So we have some changes there. So this is looking a little bit more detail at VLLM. This is how inference works. You just end up with a bunch of workers. You have a bunch of GPUs. They will all going to host a copy of the model, and then as requests come in, one tough thing about it is managing the KV cache, which is it's like the state. If you have a really big prompt with a ton of tokens, all of that allocates GPU memory, and something has to keep track of all that GPU memory. So VLLM, a big part of it is this KV cache manager, which manages blocks of the GPU memory that gets allocated as the workers need it. And then you can scale it out. So if you want to make it faster, it's actually pretty easy to make to do scale out. You're just replicating instances of VLLM that are controlling either one GPU, or sometimes if your model doesn't fit on one GPU, the workers can control multiple GPUs. But it's scale out. And VLLM does that for us. Training is I don't know what. It's a can of worms. Training on like giant clusters is a can of worms. A lot of this technology comes out of high performance computing. I learned this stuff when I was a PhD student, in like 2006 from an Oak Ridge, National Labs researcher. And we use a technology in ScalarLM that's called Slurm. Who's seen Slurm before? Is this new? Yes? Okay. Few people have seen Slurm before. When you initially look at Slurm, you think like, it's just scheduling jobs. I'm just submitting a job. Who cares? How hard is it to write like a job queue? It's not that hard to write a job queue. Why do I need some kind of framework to do a job queue? Slurm is setting up MPI, which is the high performance network stack. I don't think most people realize that. Setting up the high performance network stack is a nightmare. Like it is, I remember back at NVIDIA when we built a cluster for the DOE, I think we had a $100 million NRE cost. It was a team of about 100 engineers and a $100 million NRE cost to set up the software stack and hardware stack for one of these custom networks. It's fraught with peril. So we appreciate having open source software like Slurm that can help us with that. So the Slurm model is there's a lightweight daemon, slurmd, that runs on all the workers. And then there's a Slurm controller, Slurm CTLD. You'll see it when we run the actual workload, and it manages all of that. Slurm is really lightweight. It was built for a processor in the 90s that had maybe like 8 megabytes of RAM. So it's super fast and super scalable. You could run it on 1 million machines, and it would be nearly instant to do everything. So Slurm is very useful, very valuable. Also named by people sitting in the basement of Lawrence Livermore Laboratory, which is why it's called Slurm. Okay, so one thing that we were inspired by in this work was Megatron. So Megatron, I would say, was maybe a 3rd or 4th generation version of a framework like this. Megatron actually was a spin out of our Baidu Majel framework, where most of the engineers went back to NVIDIA, and then they wrote this thing called Megatron, which was open source. So an important thing about Megatron is that it's open source. But a few years ago, I'm forgetting exactly when this was, but this must be 5 years ago at this point, maybe a little bit longer, they showed that you can get linear scaling, which is really efficient scaling, really hard to do, out to thousands of GPUs. So this is showing that you can actually train language models on thousands of GPUs, and you can do it efficiently. So how did they do that? Kind of a core concept in Megatron is the idea of distribution strategies, which is really how do you split the model, how do you split the workload up over your cluster, over all the machines in your cluster. And they introduced these 3 kind of building blocks for distribution strategies. And I think these are still pretty good to understand. These, of course, are not the most optimized thing, but I think they're still pretty helpful to understand. So data parallelism is the starting point. It's actually probably the most widely used, most effective distribution strategy. And it does what it says it does. It splits up the data. So if you have 1 million training examples, then you're going to split it up into 1,000 chunks, and each worker GPU is going to get a separate chunk. And then they're all going to train separate versions of the model. And the tricky thing about data parallelism is that all this stuff is based on gradient descent. So it's all, the early versions of this trained many different models and then tried to put them back together. The modern version of this trains one model and actually keeps the weights synchronized across thousands of GPUs. So we'll talk a little bit more about exactly how that works as we go even deeper into that, but data parallelism is one way of splitting up the problem. Tensor parallelism is another way. This is typically what you do when your model doesn't fit into a GPU. You don't have enough memory. So you have to look in the individual tensors of the model and split them up and give part of the tensor to one GPU, part of the tensor to the other GPU. And then when they're actually doing forward propagation, back propagation, you got to go and find all the weights that you need and bring them all together in one place so you can do the math that you need to train the model. Pipeline parallelism is just you split up the model by layer. Some models have 60 layers or 100 layers. Each GPU gets a different layer. I don't think it's as widely used anymore, but it was one of the early versions of how do you split up the model. Actually, it was the first version I remember writing. I wrote a first version of this in Baidu, and we split it up over 2 GPUs. And we did it because we thought it would be easier to program. And I guess it was, but in modern world, it's not very efficient. Okay, so we have all those pieces. We can do inference. We can schedule training jobs and set up the network. We can distribute our training workload over many GPUs. We need a machine to run it on. This is an example of the machine we ran our experiments on. We're going to log into in a half an hour or so. This is a TensorWave MI300. I think these pods are 2,000 GPUs. But you can kind of see the scale, of machinery that goes into this. I sometimes look at these things and I go and look at a data center and I think like, man, that's like a battleship or like a oil refinery or something. There's I don't know if this anecdote is that useful or not. We should do this at some point. Back in Baidu, we sometimes you get like a remote access to this. So like on my laptop, I have remote access to this thing right now. So you can actually go and stand next to it while you're talking to it. And it's kind of a surreal experience. I would say when you like launch a training job and then the generators are like, you hear the power flying through the transformers and the entire thing just turns on. It's kind of like, my friend at some point, made the analogy that it's like you're a wizard, summoning like a, enormous, powerful entity to do your bidding.
You actually have a picture next to one of them.
Oh yeah, Farbod has a picture of us standing next to one of these.
Oh, I'll try to.
But yeah, so it hopefully gives you the scale of what we're trying to solve here. One of the things that's actually pretty tricky about this is when we're doing all of our rollouts to think hard about the solutions to problems so we can get training data to feed back for training and reinforcement learning. It's hard to keep a machine like this busy. If you write like a little for loop, it doesn't really work. So in ScalarLM, we actually borrow something that was originally developed for CUDA, which is the concept of massive parallel threads. So, just like on a GPU, you have millions of threads that can all be running simultaneously. And in CUDA, we came up with this abstraction. Actually, the inventor of CUDA, John Nichols, invented this in like 1988 or something. It's this kernel concept where you have a single program and you kind of map it over the whole machine. And with one op, you kind of fire up all the threads. And so you don't have to write these like little loops of like what's going to happen, or you don't have to think through what's going to happen. So we kind of made a language model interface in ScalarLM that's kind of like that, which is, we're calling it LLM Generate, but it's kind of like you're mapping all the machines over tons and tons of different prompts, or think in this way, figure it out in this way, and do it like 1,000,000 times. What we found is when we tried to run this on the regular clients, like the OpenAI client or like the regular VLM client, your loops could be like 20 iterations or 100 iterations in parallel, and then something would crash, like the number of sockets you open on your laptop would crash, or the back end like scheduler that would schedule all this stuff would crash. So we made a new interface, and you can actually submit, the biggest thing I think we've submitted is like 200,000 prompts in one shot, and I can submit it from my laptop. So that was pretty important. And then in reinforcement learning, you kind of see these like inference time trade-offs, where as you do more inference, the model gets smarter. You figure out better solutions. Sometimes these are called inference scaling laws. So if you're just doing like a few inferences at a time, you're way over here. But if you could do 1,000,000 at a time, you could move over here, and your models get smarter. And this is just a plot from an example of how we were using inference time compute to write better data-oriented code, like better database code, better SQL. So it's pretty clear, you spend more time thinking, it gets a better answer. So that's really what we use massive parallelism for in inference. So these are some of the things we added to ScalarLM to allow us to do that. We added flow control, because you have this like thundering herd thing. Like even if you could get enough laptops together to submit 1,000,000 requests, you can overwhelm the cluster. And then what happens when you take up all the memory and all the GPUs of the cluster, because they're all working on too many inference requests, you get what happened to Claude yesterday, which is the whole thing goes down. And it doesn't really work if your whole thing goes down right in the middle of your training run. So you kind of have to have an enormous amount of parallelism, but not too much. And none of the existing frameworks that we found had any mechanism to solve that. So we added in this technology that's a network technology that's just called flow control. And we added it into the framework, and so it automatically right sizes the amount of requests being sent. Yeah, and then there's also some problems of like when you're doing flow control, like how do you know exactly how much GPU memory is available? Kind of depends on what you're submitting. So we had to wire some other networking technologies back up through different parts of ScalarLM. And by doing that, we got like a 10x, almost a 10x, like an 8x throughput increase. Okay, but this is really where we ended up. We took the open telco models, we got that enormous cluster, we got all the pieces of software that I just talked about, and we trained a model on 256 GPUs, and these are AMD GPUs. People, just like that Megatron paper, have already done this on NVIDIA GPUs, but I think this is probably, I'm not completely sure about this because I don't know what people are doing in secret, but I think this is, as far as I know, the first biggest post-training run on AMD ever, where we trained on 256 MI325 GPUs, and we got a 240 times speed up. And yeah, it was a long time coming. It's actually very hard to do these things, but today we're on the other side of it, and today, this is something that's already happened that you could just use. Okay, so we're going to talk a little bit about how we did this. All right. So I'm going to talk a little bit about post-training and some of the, going a little bit lower into how we actually ran this run. I talked about the software pieces at a very high level, and let's just go maybe one level deeper if you actually wanted to run this yourself. That's the thing we're really working towards here. We're working towards understanding at the high level, but also down to the level of you need to push the keys on the keyboard, you need to run this yourself. That's what we're going to try and go through here. Okay, I'm going to pause just for a second because we're switching, sections, and I just want to see if there's any questions or comments from anybody as we're going through here. Okay, I'm going to pause for one more second. Oh, there's a question. Okay, over here. Here. I feel like I'm going to need a. Yeah, thanks. You gotta turn it on.
Yes. So, what were you referring to with our?
Oh, is it on? Can you hear it?
You gotta turn it on.
Okay. Thanks.
Yes. Okay. Thank you. Yes. What were you referring to with RNJ? RNJ.
Oh.
Yes.
Yes. RNJ is, I think it's pronounced range. It is a pre-trained model from Essential AI. That is the transformer inventor, also invented Range 1. It's, I believe, the first open weight trained in the US language model that was trained on AMD. So we're one of the themes that we're showing here is GPU agnostic. And we're going to talk about many models here, like including Google models, including like NVIDIA models. But Range 1 I think is pretty interesting because it was trained on a cluster just like the one that I showed you there. And we're not talking about pre-training here. Ashish I think is going to join us in a little bit to tell us a little bit about how Range 1 was trained. We're mostly talking about now it's previously been trained, now we're going to further train it using reinforcement learning on the cluster here. There's a question over in the back.
We can hear you.
Can you hear me now?
Yes.
Thanks, Greg. So you've done large-scale training on both NVIDIA and AMD. Can you just talk through some of the key findings of the differences across the two GPUs, something you want to flesh out in that experience?
Sure. Differences between NVIDIA and AMD training. I think we'll see it here. I mean, I think one of the things that you're going to see is that the interfaces at the ScalarLM level at this point, in 2026, are pretty similar. We actually, if you're building your application on top of it, and we'll see what the interfaces are. If it's just you're submitting training data and you're taking training steps for training, or if you're like that batched inference interface that I showed, if you're at that level, there's no difference. There's definitely going to be, as you're bringing up the infrastructure, and we'll actually do that in the later half of the presentation, you're going to see some of the, just there's certain things about like the machine shape, or, there are really different processors themselves, so the processor details themselves kind of come up a little bit. But yeah, I think one thing also that's worth mentioning about AMD is AMD has a lot of memory right now. And so it's actually easier to fit really big models. But yeah, I'd say the overwhelming message is it's mostly the same if you're at this high level. But then as you go lower level, you may start seeing more differences. We'll see some of that. It's a good question. Okay. I think that's totally fine for now. I just want to make sure we had a chance to be a little interactive, but let me move on to the next section, and then we'll have more opportunities to ask questions as we go. Okay. All right, so let's look at post-training. I think this figure is a good one to start with for post-training because it's showing this algorithm that was introduced in DeepSeek that's called GRPO. I'm not going to expand the acronym. I just talk about them with the acronyms. But I think it's pretty simple. It's really, instead of just trying once to solve the problem, you're going to try multiple times. So if you've seen the current generation of language models, you'll know that they think before they deliver a response to you. So here, this is showing you have a question, it's showing the thinking tokens. The model is just going to be, generating, sometimes we call these reasoning trajectories in reinforcement learning, sometimes they're called reasoning paths. But really they're just different ways of solving the problem. And so you let the model try and solve the problem multiple ways. At the end you have a reward model. It's a very fundamental piece of reinforcement learning to have a concept of a reward model. And the reward model tells you whether or not you got the right answer. So sometimes I think people find it hard to understand what a reward is, but I always like to pick a simple example, like imagine you're just writing a computer program, and then at the end of it you just press the compile button, and sometimes it crashes and sometimes it doesn't. That may not be the best reward model in the world, but that is an example of a reward model. Okay, so in methods like GRPO, we're exploring many trajectories simultaneously, and then after we've explored many of them, we're going to update the model. We're going to take a back propagation step and apply gradients and then update the weights of the model. So this here is kind of like one level down of exactly how that works in ScalarLM. So at the top of here, you've got some text. This is what came out of your reasoning trajectories. Some input text and some output text. This is like if you're using a language model, like your prompt, and then what the model responds with. Input is like the prompt, output is what's generated by the model. Sometimes in reinforcement learning, you also have a score that usually comes from the reward model. You don't always have that. I would say sometimes the text itself is the score. Like you could include the trace of whether or not the thing crashed, and the models are able to read and they know whether or not it crashed. So sometimes you need an explicit score, sometimes you don't. If you're just getting started out with this, I'd recommend not, because it's a little bit more technical to understand how to scale this number, how to determine exactly what this number is. But it's there. Sometimes these frameworks have it. Okay, so that's what your training data looks like for a step. So then how does that, in ScalarLM, how does that get mapped to GPUs? This is the interface that we have in ScalarLM. So you're kind of like just making a list full of some inputs and some outputs. They're just strings. And then you're saying train. You're calling an API that's like LLM.train. And then the result of that is you're going to get an updated model. Okay, so this figure here in the middle is kind of the intermediate representation. We got to convert everything into tokens. The model doesn't really work with strings or text, it works with tokens. Tokens are just, there's a tokenization process, and it's usually just a dictionary. So imagine that it's like looking up the word in a dictionary. What page is it on? That's kind of what a token is. So when you're doing training, part of stochastic gradient descent is the S, stochastic, that means random. And so when you introduce randomness, we do this shuffle. So you need to actually like shuffle your data around, because if you just train on the same thing over and over and over again, the model overfits on it and it doesn't train as well. So the typical way of doing this is just you got this list of all this data you want to train on, and then just randomly shuffle it. So randomly shuffle, convert into tokens. Now once we got the tokens, we need to send them to different GPUs. So in here, and this is like hypothetical simplified example, we got 2 GPUs, and we need to break down the tokens into pieces that can be sent to each GPU. So there's a lot of different ways of doing this. I think this is one of the better ways that I've seen. But all this source code in ScalarLM is open source, so if you don't like it, you can always rewrite the entire thing. It's just a few hundred lines of Python. But this is kind of how it works. You kind of take all the data after it's been shuffled, you put it together into a really long string, input, output, just back to back, super long string. And then you get this really long array of tokens. So this like blocks here in the figure are tokens. And the colors just mean they came from like the input or the output of one of the original training examples. So then what you do is it's kind of like a filter operation. You first break it up into chunks, and we like the chunks to be evenly sized, because if they're not evenly sized, then you got some serious problems with getting good utilization out of your cluster, because all the machines are all working on different amounts of work, they all complete at different times, and they all get out of sync with each other. So it ends up slowing things down a lot if you got to bring them all back together when they're all out of sync with each other. It's called load imbalance. In high-performance computing, it's called load imbalance. So we hate load imbalance, so we break up everything into evenly sized chunks. But what that means is that some of these examples are kind of spanning chunks. You can kind of see like here, the output of the first one got chopped in half. The way you overcome that is by random sampling. So if you do this enough times, the odds that your particular example that you really cared a lot about are going to get split exactly in half, go to 0, and you end up being completely fine. One of the things that this also avoids is padding. Like if you've ever written one of these things, you had to think about padding. It's just like an enormous source of complexity. Padding also messes up the way that your model trains. So if you don't really know whether your gradients are being applied where, how to compensate for that, we find this way is just way simpler. You don't have to think about it. Okay, so once you've broken up all of your data into chunks, so now you have even-sized work, you need to send them to GPUs. Maybe the GPU wants to work on more than one at a time, batching, in SGD, one of the parameters is the batch size. So you can have these purple boxes that just collect up a bunch of chunks together into a batch, and then the GPU will take a training step, and then you've updated your model. Okay, so this is kind of how the data gets from your reasoning trajectories into the input into your model on each GPU. Oh yeah, and if it's not already clear, different GPUs are going to be working on different batches simultaneously. So you've got 1,000 GPUs, each one is getting its own batch. They're all figuring out what the update is according to that batch, and then you apply it all at once. Okay, so this figure kind of makes that a little bit more explicit. In a epoch, which is like a pass through the data, maybe in this case batch 0, batch 2 kind of go to the first GPU, batch 1, and then over here batch 1 again, go to the next GPU. One of them comes from here, and then one of them comes from here. Because you may run out of data, so you just fetch from the next epoch. You want to make it all load balanced. And then every single one of these steps, you're going to do an update to the model. Okay. So that's how the data is split. And then one thing I didn't mention is how do the models synchronize. All the different GPUs have their own version of some weights. You need to make sure that they all agree with each other. Otherwise, you get 1,000 different models rather than one model. You want one model. So we use this kind of technology that was like the thing that I mentioned in the very beginning of the presentation. It's usually called a collective. It comes out of high-performance computing. In data parallelism, where every GPU has its own copy of the model, we're just giving it a different piece of data. We typically use this collective called all-reduce. I'll explain what that one is in a second. But here's kind of the intuition for it. A GPU has the data. You're going to do forward propagation. Forward propagation generates, what the model was going to do. Maybe it was right, maybe it was wrong. You backprop an error signal through it. You get a gradient. I don't know if anyone's taken like Andre Karpathy's 0 to Hero. You kind of walk through exactly how to do this. But you end up with a gradient. The problem is that every GPU has a different gradient. So you use an all-reduce, which is, it's mathematically not very complicated at all. It's just you're averaging, effectively, or you're summing, or you're averaging the gradients across all the GPUs. And it's just really tricky to do this over a network because it's very easy to do this slowly. It's very hard to do it very quickly, efficiently. So that's why we have these collective algorithms. The algorithms themselves are pretty sophisticated. They're very unintuitive. I think my experience in Baidu of when people looked at this stuff, almost everybody thinks you should do a reduction with a tree. But it turns out that you should actually do a reduction with a ring. And that's very unintuitive usually, even to people who are good at computer science. So we want to use our collectives. We've done our collectives. Now you can apply your gradient step and update your model. So there's also this footnote over here in the corner, which is when you're doing this, depending on which optimizer you're using a different amount of memory. So depending on if you're training an enormous model or a smaller model, you may want to use these different optimization methods. Some of them converge faster. So like Atom over here is actually keeping multiple copies of the gradients, which all take memory. And so they can run out of memory if you're training a really big model. So you can actually dial down the optimizer back to just regular, Nesterov, SGD, or these intermediate things like eta delta that converge. They can converge just as fast as Atom, but they usually require more fiddling. You may have to adjust all your hyperparameters really aggressively to get them to converge well. But then they take less memory. So there's all sorts of optimizations. Maybe it's hopefully getting kind of clearer. Like as you go into this, you have to think about a lot of different pieces of this all simultaneously. Also, one other one over here we're kind of showing here. There's a choice of, for all of the different parts of your model, what precision you store them in. The reason why it was so hard to introduce tensor cores was because if you just convert everything into low precision, the model completely diverges and training doesn't work at all. So these hybrid, mixed precision formats get introduced, and they end up being very complicated and very sophisticated. Like at this point, probably the state of the art is around 4-bit formats, but that doesn't mean that every single thing in your network is 4-bit. You're kind of selectively applying it only in particular places, and if you put in the wrong place, the training will just not work, or it will be massively slower than if you got it right. So hopefully it's clear. There's a lot of different knobs here that you can turn when you're training, and you kind of have to turn them all correctly, otherwise it doesn't work. Okay, so the last thing I'm going to put here is just maybe those are some of the building blocks that I was showing previously. This is kind of building up to a more modern method, like FSDP or fully sharded data parallel kind of puts together tensor parallelism with data parallelism. So you can simultaneously split up the training over a lot of GPUs, but also train models that don't fit onto single GPUs. And I think it's actually, I'm just going to take a minute or so because I think it's worth looking at this. There's a lot going on here, but the basic building blocks are pretty similar to what we've seen before. The collectives do change a little bit. Instead of just doing an all reduce, you still have an all reduce. You have two other collectives. One is all gather, which is all of the GPU is gathering up all the weights for the particular layer so that it has all the state that it needs to do forward propagation. But then, because that takes up a lot of memory, as soon as the model was done with that layer, you throw it away. And then during back propagation, they all end up with a individual gradient, and you have to kind of pick out the pieces of the gradient that the particular GPU has, that correspond to the weights that the particular GPU has, and that's a scatter reduce. So you end up with these different collectives. If you look at MPI, like high performance computing, there's a library of about 20 different collectives. And so you can kind of see that as people are building methods like this, they're drawing out of the whole library of these collectives. Okay, so this is what maybe like a more modern, realistic training algorithm would look like. Okay, so with that, hopefully you kind of understand some of what's happening under the hood in training. And one of the things I think is, it's still not perfectly abstracted, I would say, in high-level frameworks, is it's like, well, do you have to actually think about this stuff? Yeah, you kind of do actually have to think about this stuff if you're training a model like this on a machine like this. Oftentimes, a lot of what happens is you get a model that doesn't quite fit, or you get a model that has like a particular change in architecture, like it's doing, mixture of experts using a particular like way of activating the experts, and you have a question of like, which weight should I gather? And it's not the same answer for every model, and it's not the same answer for every machine. So we'll look at some of the programming abstractions that you have to deal with this, but you do have to understand this stuff and be able to kind of move these things around if you want to train a model like this. Okay, so I'm going to pass it over to Farbod to actually look a little bit more at the training code. So I told you about what kind of models we're training, how we're training it, software stack that's being used. But now let's actually look at some code that actually trains a model.
I think Ashish is about to join the call.
Okay,
maybe, maybe we do it slightly differently. I was, Can you let Ashish in? He's in the waiting room. So, one second, let me make sure. Oh, perfect. I was planning to go over the ML directory. Let me share my screen real quick. Hi, Ashish. Oh, we can't hear you, Ashish. Can you guys hear? Hold on. We can't hear Ashish. 1 second, sorry. We have some technology difficulties here. Give us a minute, Ashish, sorry. We can't hear him. Oh, that's the microphone. I think we can put the speaker on something else.
This is okay. I'll be able to stream.
Oh, can you guys, one of you unmute for a second? We want to test.
Yeah, test.
All right,
Testing.
perfect. We can hear Philip. Ashish, can you also test for a second?
Hi.
All right, perfect. Awesome. It was perfect timing. Greg just explained FSTP, and he talked about like the ScalarLM history. We are right at the moment. We actually want to go over the ML directory and we show how we train the range model. So we would appreciate if you guys talk about range model and give an introduction. Let me just. If you want to share your screen, if you have a slides, or otherwise, please just go ahead.
No, we actually do have slides. We came somewhat prepared for this. Let me share. So Philip, I will share my screen and then I'll hand it over to you. Then you share yours instead of us. Okay. Allow. So we don't normally use Microsoft Teams, so I hope that I'll be able to share in one button. But okay. Presenter mode. Screen. Can you all see my screen?
Yes.
Okay. So, all right. Hello, everyone. So I will start the presentation, and then Philip will continue with some more details on our pre-training. I am Ashish. I'm the co-founder CEO of Essential AI, and we are a company based in San Francisco, California, and our mission is to close the gap in between open source and the frontier models, or we want to build open source, open weight frontier models. And I'm going to give you a brief introduction on Range 1 from Essential AI, and it is a new standard for American open weight models. First, obviously, the naming. Range 1 has folklore, and it is named after the Indian mathematician Ramanujan. And well, actually, it shouldn't add. I didn't mean to add a -1 there. It's named after the Indian mathematician Ramanujan, not Ramanujan 1. He was not an alien. But our specialization, our models are we focus on STEM and code. A lot of our backgrounds are researchers and scientists. Gives us because of our backgrounds, STEM and code really appeals to us, and also a lot of the important applications that we care about fall into they fall out of the core competencies in reasoning about STEM subjects and being able to code. So I'll immediately jump into some of the results. Range 1 is a 7B model. I don't know if Farbod and Greg shared that, but in its weight class, it performs at par or better than the other existing models, and also for about sometimes even about a fourth of the actual training cost. For instance, our base model, Range 1 base, was about a fourth of the training flops as Qwen 3.8b base, and actually on coding benchmarks like MBPP and Human Eval. These are Python exercises. We perform. We sometimes outperform or we're very competitive. And on math benchmarks with the base model, Qwen 3 slightly better, but compared to other open source models, for instance, Llama 3.8b or Gemma 3.12b, we outperform them in, I believe, all cases. In a sense, we significantly accelerated, or we're delivering you one of the best 7B models, or 7 to 8B models in the world, and it was built in America. And on the instruction, and we also obviously instruction tuned these models because we wanted them to be competent at reasoning in math and agentic coding. And here we again see that our models shine on the classic Python exercises. I like MBPP and Human Eval. We see significant improvements. Again, sometimes outperforming competitive models in the same weight class and even larger models such as GPT-OSS 20B. So, for instance, on MBPP, we're about at par with GPT-OSS, a much larger model. Although I don't know what the activated parameters for GPT-OSS 20B are. Does anybody know? Philip, do you know? Probably less, very likely less than 70.
3 or 4, right?
Yeah, it's a mixture of experts models. So I wouldn't know if not an exact comparison in terms of activated parameters. I think that probably we're twice the number of activated parameters. But for total, we pack per parameter as much intelligence. But where we're most attractive, I would say, is if you go down to Sweetbench Verified, which is for a while kind of been the litmus test for agentic coding. We're at 20%, which significantly outperforms any of the other instruction tuned models in that same weight class or even larger. And this reveals the effort that we put into ensuring that the model was very proficient at understanding and generating code. Another area that we care about is performance optimization. Ultimately, we want our models to be used for autokernel generation and understanding the performance behavior of code is important. And we instruction tuned it for a benchmark that actually that measures how well your models can iteratively improve the performance of code, and we do quite well there compared to other models in the same weight class, and also tool calling, which is obviously a really important ability if you want to use if you want to deploy these models at if you want to use them for computer use. I guess that hopefully gives you a picture that if you're looking for a smaller model that even runs on your laptop, that does well on coding and math, range one is a good choice. And just kind of gives you a picture. So this is not. I'm sorry. It's from. This didn't happen instantaneously. So this is from. So from range 0 to range 1, but this sort of depicts what the progress has been over the last year, and I think Philip is going to dig some more into the share. This is like a vignette of what happened over the year, and Philip is going to share some more details on the pre-training side. But range 0 was our first pre-trained model, and I believe we concluded pre-training for range 1 around in July, and we obviously improved significantly on all measurements that we cared about, both on the capability side, but also very importantly on the infrastructure side too, and allowing us to maximally utilize our cluster and recover from any interruptions to training, which is critical if you're training a model on very large. If you're training a model on a large distributed cluster. And this year, we're obviously excited to advance, go beyond 8B models, and we're planning to later in the year release larger mixture of expert models that are significantly better at the abilities that we care about. Obviously, this is work by a great team, and won't be able to go over everyone's names, but they were about 21 core contributors to range 1. And they're fantastic teammates and leads. Philip leads our infra here. You'll obviously be he'll be speaking with you soon. And please check out our website. You'll also see some of the videos from range 1, some demonstrations of its abilities and how we act. We also connected it to open source editors like Klein. But range 1 is obviously the culmination of a lot of work that we've done, and there were many independent individual research pieces that went into range 1. For instance, one of the choices, maybe contrarian in early 2025, that we made was that pre-training or compression is where you need to start, because pre-training imbibes all the core abilities that eventually specialize. So we kind of started at we had this thesis that if you can master pre-training, then post-training, then you'll be able to train much better post-trained models. And one of the papers that kind of demonstrated, empirically validated our thesis was this paper on reflection that claimed that you can identify these reflection abilities where models sort of pause and rethink what they've actually rethink their work, and so that they correct it midway. This ability to reflect actually can be detected and is picked up in pre-training. So this gave us conviction in our this was one piece of evidence that gave us conviction in pre-training. We also another big open source contribution, perhaps our most popular open source contribution that we've made, is releasing a 24 token data set which is labeled with a very rich taxonomy, so you can pick and choose which documents you actually want if you want to fine tune it for different use cases. Please check out the paper. And also we were among the first to present the superiority of the muon optimizer over Atom, which is what we use to train both range 0 and 1, I believe. Yes. All right. I will stop presenting and I will let Philip take over. Thank you.
Thank you.
Great, thank you. Let's see, let me figure this. All right, can you see my screen?
Yes.
Great. Yeah. So yeah, I'm Philip Monk, and I lead the infrastructure team here at Essential, and so I ran the infra effort to train Range One, and I know this session is mostly about fine tuning, but I'm hoping I can give sort of a taste of what it's like to pre-train these models. And I know we haven't spoken publicly much about what that process was like, training on these AMD GPUs, and so yeah, I'll be glad to share some details on that. Pre-training in a lot of ways is more demanding than both fine-tuning and inference, mainly because of the scale, right? You're training on hundreds or thousands of GPUs. You're often training for weeks at a time or even months. And so there's a lot less sort of margin for error. Anything that that happens 1 in 100 times is guaranteed to happen several times, right? And so because of that, you have to expect and plan for hardware failures, network interruptions, um, software issues, whatever might come up will happen, and it'll probably happen while you're asleep. And if you're not careful, you'll end up, delaying your run by a week or more, just in wasted time. When you've got the whole cluster reserved, but you're not making any progress. One of the things also that makes a difference is that in training, all the computation is sort of interlocked. If you have some compute core somewhere that 1 in a billion times produces NAND when it shouldn't, or some kernel that has some slight instability, in inference you might not notice because once a day you'll have one singular prompt that gives an error, and the client retries and nobody notices. But in training, you will notice because it'll immediately, once one NAND shows up, your loss will be NAND, and then all your gradients will be NAND, and within 5 seconds, everything you're doing is NAND. So everything is interlocked a lot more. Everything has to be right. The margin for error in your hardware and your software is a lot smaller. So range one, as Ashish said, is a 8 billion parameter model, which we trained on more than 5 trillion tokens over a period of about 3 weeks in September and October of last year. And we trained it on 768 MI300X GPUs from AMD. We have been training on AMD GPUs since 2024. We train on other accelerators as well, but for range one, for our flagship run, we trained on these AMDs, and we have been doing this for a while. I think we may have the first dedicated training cluster on AMDs, as far as I'm aware. And so in that time, we've gone through a lot of learning and a lot of improvements on how to make this stuff reliable. And that's a lot of the stuff that we learned, we've gotten better at, but also the public ecosystem for training on AMD GPUs has improved massively. There's a lot more sort of understanding of how to run these GPUs, how to run them for training, what kinds of failure modes you should expect to see, and also just the sort of the getting started software is in a much better place than it was when we started. But I certainly enjoy the journey of getting to this level of maturity, and I'm glad we learned a lot. Now, Range 1, of course, is our first publicly released model, but we did train models internally at a similar scale. The Range 0 that Ashish referred to, it was in early 2025, and so in that process, we, a lot of those early training runs, we tried to just send it basically and see what happened, and it was pretty rocky in a lot of ways. We had a lot of interruptions, some on the hardware side, some on the software side, some that we could auto recover from, but many that required manual intervention. And so that was a big focus for the infrastructure team, was to reduce the amount of wasted time of bad put. This is time when you have the whole cluster reserved, but you're not training for whatever reason, because there was some interruption, you're in the process of recovering from it, or perhaps you're retraining the same steps because you're recovering from a checkpoint. All of that is wasted time. And we took that from being, in our early runs was about 16% of our time. By the time we got to training Range 1, it was less than 5% of our time, which we would still like to get that number down, but that's already a much better place to be. And yeah, a lot of those improvements really came from working on the fundamentals. We didn't do anything sort of really groundbreaking here. You just have to be, like everything that we do at Essential, we do kind of from first principles. We pre-train from scratch. We think of this stuff from first principles, and so you have to sort of do the basic things that are required to make a job like this run smoothly. At a small scale, you can cut a lot of corners that you really can't at a large scale. As your scale grows, the ability to sort of solve problems ad hoc and then move on goes away, and you have to, anytime that an interruption comes in, you have to classify it as, is this something I've seen before, something I haven't seen before, and come up with a solution that'll work for this issue and any that come in the future that are similar. And ideally operationalize that into something that'll automatically recover. This is especially true with a small team. We have 4 infrastructure engineers, and that means and infrastructure is a lot more than just running a cluster. So we can't be spending our time dealing with with interruptions constantly. So we have to sort of solve this. The 2 biggest things that we did that made training Range 1 a lot smoother is we came up with a battery of tests to determine if a node's hardware is healthy. And this is super important. You really just have to have this, because if you're running, a 32 node job or something, and you have a failure, you might not know which node is the issue. And if you can't narrow that down, you just try to start the job again, and it'll take hours to try to bisect into your nodes and find out which one the issue is. But if you have a battery of tests you can run to identify which node is the issue, then you can just start that, and you don't have to worry about anything else. And these tests don't have to be super complicated. Right? The set of tests that we use for Range 1 and we use now is just these 3 tests, right? We have a single node stress test that tests the HBM, the compute cores, the PCIe bandwidth, HDMI bandwidth, all of that. And that we were able to get from AMD. We did not have to write that ourselves. That one makes a big difference, but of course there are issues that will happen between nodes in the networking. We have a very simple Rickel networking test that you just give it 2 nodes, and you have them try to talk to each other, all the GPUs on one, try to talk to all the GPUs on the other, make sure you exercise all the connections. Takes about a minute to run. That catches most of your networking errors, either because they can't communicate or maybe the bandwidth's too low or something like that. And then the third thing is we run a 2-node end-to-end training test where we'll take a couple of nodes, the one that we're testing and one known good node, and we'll do a short run on our actual training stack. And this will flush out any final issues, any software misconfiguration. It's the most similar test to our actual workload. And so when we run these 3 tests, we have very good accuracy of whether a node is actually healthy. I think we've had only one node that passed these 3 tests that actually had a hardware issue, and we're still looking into that one to see what's happening with that. But it's an almost perfect record with that. The second thing we did that made a big difference is we were originally streaming in our data from from another cloud provider where we keep our permanent data and where we do our CPU jobs, where we transform our data. And we were also writing our checkpoints back out to, over the internet originally, and then over a dedicated interconnect later on. And this ended up being a source of a number of interruptions, a number of hangs. We ended up simplifying by saying, actually, you have to download all your data into the cluster before running the job. You need to write your checkpoints to a local shared file system, and then we'll have an async job in the background, moving that to permanent storage. But this means that your training can continue regardless of any interruptions in the network, regardless of anything that's happening outside the cluster. We had a number of network disruptions, sometimes for hours at a time, and training was able to continue without interruption, which makes a big difference. So the impact of these kind of changes, you end up with reduced node failure frequency because you can isolate failing nodes faster. We had a lot better automatic recovery than we did originally. A lot fewer cases where it would just hang, because if something crashes, we can retry. If it hangs, you need something to kick it, right? And the last thing that we got from this is much faster startup times. Startup times, should be just a few minutes. When we initially tried to scale this up, startup times ballooned to over 45 minutes, partially because of networking related things, but just kind of other things we didn't anticipate. And so getting that back down to sort of the 7-minute range made a huge difference, because when you're training these, especially subjectively and selfishly, if I'm about to go to bed and I check the training run and there's some issue and I need to restart it, there's a big difference between in 7 minutes I'll see that it's working fine versus okay, I'm going to be up for another hour, and hopefully it worked, because otherwise I'll be up for another hour. So solving all these issues definitely helped me sleep better at night, in a pretty literal sense. So in summary, pre-training is in along many dimensions more demanding than both inference and fine-tuning, and so you just have to follow discipline practices to reduce the frequency of failures, to reduce their impact. But if you do that, then your training can be a lot smoother. We ended up in pretty good shape on these, and we're looking forward to training on a larger scale, where these lessons will be more important, and I'm sure that we'll learn even more. Thanks.
Thank you very much. Let me ask the room if anyone has any question. Any question for Ashish and Philip here? Oh, we do have a couple of questions, Ashish, if you have a minute.
Oh, okay, sure, yeah.
Can you hear me okay?
Yes.
Yes.
I'm not sure Ashish will be able to hear me, but With the range models very focused on maths and agentic, I wonder if there was a focus on multi-languages. So we do a big project in Africa. Are you focusing on all of the 7,000 languages in the world? I know that's your sort of background and your research basis. So I wondered if you have plans to look at language as well as coding and agentic.
Right. So although between all the members in the company, we do speak a bunch of languages. We're very diverse. We're a very small. We're a very small team. So part of one of the philosophies behind the success of being able to get to the result, get to range one, a very a world class, at least in its weight size model, was that we had to focus very fiercely on only a few directions, and as a result, as a result, we couldn't take on some very important abilities such as multilinguality, right? In the future, we absolutely want our models to be conversant and fluent in multiple languages. But on our roadmap, I don't see us focusing on multilinguality for 2026. Our roadmap is still quite concentrated. I mean, essentially, what we want to do is we might want to stick with the same breadth, but maybe add one or two other domains, such as the financial domain, integrate those into the abilities of the model, but we want to push for much greater depth in the existing abilities that we have. That's how I would describe our goals for 2026. That's where we would dedicate a lot of our research efforts. But we consider extending the language set to be very important. It's just we might not be able to make progress there in the short term.
Hello, thanks for the presentation. I have two questions. Maybe one is out of scope, but I was curious about what is the financial strategy for this type of projects. I mean, I think it costs greatly to train one of these models. Maybe also to train the next iteration might be costing the same amount or a little bit less. But I don't know what's the plan. How is the funding or done and the amortize the return of investment as well, like planned for this?
Right. So we're charging for this tutorial, so that's one place where we start. No, I'm kidding. This is a good question, and that's definitely one of the challenges that we have to address. But I'd say that there's obviously we're not going to reinvent the wheel here, right? There's the streams of revenue are going to be either deploying our models in marketplaces, revenue sharing through that, or custom deployments, or working with system integrators and that's kind of one sort of maybe category of business models. The other is that we actually focus on specific real world applications, and that's where we're attending, and we're in conversations with choosing a vertical. And as we push our models to the frontier, we also have a source of revenue from a particular vertical. So I wouldn't say that we're not reinventing the wheel here. So it's either a specific vertical or it's working with doing custom deployments or marketplaces.
Okay, thanks. And another question, this one a little bit more technical. Or what was the type of coordination between the teams and the work done for this project that took several weeks, months? While you are training, you are mostly consuming I don't know if all of the resources. What else can the team do while it's training for weeks, for days? Do you? I would guess that you would have to start working on the next thing, but the next thing needs also the resources to be able to run.
That's a very good question, by the way. Um, and so we earlier in the year we actually earlier in the year we prepared some research bets that we were going to focus on. So we knew in advance what are the we knew in advance what are the uh, where we would put our efforts, and Essential has a few pods. I don't think we got a chance to. I mentioned some of the pods there. We've got a optimization pod, a code pod, infra obviously that Philip leads, and then a pod where we focus our research on acquiring STEM knowledge and reasoning capabilities. So, and each one of these pods, we articulate our bets, and we are always working in parallel. So what we do is we ask we hypothesize some important research questions that we need to ask. If you're successful in these, if you're successful, then they will advance the capabilities of our model. So we have a portfolio of these questions. We pick the ones that we pick the ones that we believe have the greatest, we balance risk and reward. And at the end of like 3 to 4 months, we handpick all the best the best advancements we've made, and then we kind of pour it into our flagship run. We do have another cluster of a research cluster where we're always keeping it. We're always utilizing it for some of our shorter, faster faster iteration experiments to answer these research questions. So it's not just this cluster. We have another, but it's a smaller one in terms of flops. But that's so research bets, and then as based on the successes of our research bets, we handpick what's actually going to go into our model, and we have another research cluster that's constantly active to answer some of our smaller research questions. I hope that and coordination. We're not a very large team, so we all are very collaborative, but having pods with concentrations always helps. And I don't know, Philip, if you want to add anything about the infra pod, but sitting all next to each other also helps a lot, as the infra pod does.
Well, about the infrastructure, I was also.
I think it makes a big difference to have the whole.
I was also, if you can add into it the failing, maybe about the failure modes or the most recognizable failure modes.
One room, I think, makes a big difference. You're muted, Ashish.
Could you repeat that one more time?
Yes, if you're going to talk about infrastructure, also about the failure modes or the most recognizable failure modes that you had.
I have one, but I have one that I have one that we've had to that has constantly been a thorn at our side, but I'll let Philip go first. Yeah.
Yeah. The failure modes, once you have a job running, the failure modes that we see the most are actually now just hardware failures, which is actually the point that you want to be at, because we used to see a lot of software failures, things that were sort of more our fault, and we don't see a lot of hardware failures, but the most common one there is just an HBM issue, some ECC check failure or something like that. Doesn't happen super often, but it definitely happens. In practice, we often end up though wasting more time just in the coordination phase, the scheduling phase, especially when it's one large run. That's actually becomes a lot simpler. When you have a bunch of people trying to run a dozen different experiments, some of them using entire nodes, some using partial nodes, that orchestration is still something that people will walk up to my desk and be like, "Hey, I submitted this job and it's not running," and then I go figure it out.
What I would add, whatever I'm going to add, I think has to do with the inherent uncertainty of research and how and it appears in um, it, the challenges appear in many forms. One is, how confident are we about the answers at smaller scales? We're not blessed with an enormous number of resources, so we have to be very careful in our experimentation. And when we choose, quantifying success at smaller scales can be challenging, and you have to carefully measure, and you have to measure and at times, and to the best of your ability, whether your result is going to generalize at larger scale, right? The results that you're discovering are the invariants to larger scale. So that's one. Another one, and this has been, and we're constantly getting better at it, but maybe this is this is probably an analog of feature creep in when you're building products, is deadlines, when you're going to start the run, when you're going to start the run, that precise date. Setting that precise date can be challenging because of the uncertain nature of research, and because you always want to reach out for the last experiment or method that you believe is going to you believe is going to advance the capabilities of your model. So having the discipline to I don't know, tape out all your research, or make sure that everybody has the methods in by a certain date is challenging. I would say so. So planning has been planning for the start of the flagship run is we're getting better at it, but it has proved to be a challenge.
Awesome. Thanks for sharing.
Do we have any more questions?
Yeah, I have a question. In the last weeks, I was working on trying to benchmark linear attention and gated delta nets or delta networks. And I was wondering if in your small scale clusters you were also experimenting with some type of state space models or linear attention.
We are not, but we are hoping to soon release a long context model where we'll share some of our approaches there, but we're not looking into state space models or linear attention yet.
And then, I mean, I'm studying my master in AI right now, so I want to kind of ask like a selfish question. When you would be in this position, 23 years old in this master, what research topics would you focus on in order to learn as much as possible about this space? Or is it
I don't
the
know.
right
I
thing
mean,
to focus on?
I think so. I think you will appreciate you will appreciate the maybe different perspectives that Philip and I have here, but I don't know if you'll agree with my answer, but I would still say that I would focus on computer science itself, and trying to fortify the fundamentals as much as possible, right? Deep learning isn't, unfortunately, there's still so much that is relatively unknown in deep learning compared to other fields, but still trying to learn it from the ground up, and ex- and exa and also, um, I would say be aware of the progress, since and how some of the methods evolved is helpful, so that you can understand how many of the techniques have gotten to this current point. So I would say that it's probably important to strengthen to still stick to the fundamentals as much as possible, and have a broad understanding of how advancements have happened in deep learning, to get a sense of how progress typically happens. And there's still a lot on. I expect that we will continue to see and make advances. And obviously there's tons of other very and the other last thing I'll add is that I personally my personal view is that um, modern AI is like building a plane. It's a systems problem, and you see a lot of advances in this no man's land between, or co-evolution of, architecture and hardware. So this is a great opportunity for you to integrate knowledge from various fields, and make decisions that bring in isn't a law, but typically bound by how well our models can learn through gradient descent. But we're generally operating under many constraints, and I guess physics. Philip can also talk about he talked about many of the constraints that we operate under. So we have this kind of great opportunity here to do a lot of research between fields, and that's where a lot of advancements, I think, have happened and are continue to happen. That was my last point.
Thank you.
Philip, I don't know if you wanted to share, because I mean, you also came from a different background, so and maybe you have a different view than I.
Yeah, no, I basically agree with that. I come from, I didn't study AI in school, right? I come from a more traditional computer science background, some programming language background, and everything here, I mean, it's just a computer program, kind of, right? And to the degree that you can get good at that craft, like that's always going to pay dividends. Everything that we're doing is learning how to use, how to create programs that do things well, right? So I definitely agree that getting down to the fundamentals of how exactly are these things trained, how exactly does inference work, um, which parts of that are the most expensive, why are they expensive from a sort of an algorithm's perspective, from a data flow perspective. Just try to get into the nitty gritty as much as you can. Any instincts to be like, oh, well, that seems complicated, seems too low level. Why would I care about that? Try to, suppress those instincts, and instead, let your curiosity sort of drive you to understand. Okay, well, how does this part of the process work? How does that part of the process work? Because the whole thing is, it's both a science and sort of an operation, maybe not an assembly line, but it's a process, and it's worth sort of taking that aspect of it seriously.
I completely agree with that, and maybe one thing that is one very critical aspect of what we do, that probably isn't introduced or addressed as much in in college and graduate studies, is measurements. We've spent a considerable amount of time building careful evaluations, sometimes external, sometimes our own internal ones, like being very precise and being precise and surgical in measuring abilities of these models. And you can never have enough evals. I'll say that you can never have enough evals. I would call it a craft. It's a very it is a challenging craft, and you have to be very intimate with the model, and also understand and constantly be clear about what you're trying to measure, and that ends up paying a huge dividends. We've benefited a lot from having like measurements as careful as we can construct. Yeah.
All good. Awesome. Ashish, Philip, thank you guys very much for joining. And I think, should we take a break and then move on to the coding part? What do you think?
Yeah, I think it's a good idea. At
Okay.
least get up and stretch a little bit.
Yeah.
But
Ashish, feel free to hang around, but like, we're gonna take a break and we're gonna come back, and essentially we're gonna go through like how to train range one at a scale on 200 GPUs. It's gonna be like coding for the rest of the session, but thank you all very much for joining.
Thanks, guys. Really happy, really, grateful for the opportunity to talk about our work, and congratulations on all the fantastic results for both. And also, kudos and hats off to Greg for, I would say, pioneering two platforms, NVIDIA and AMD. So before we started, the fact that Greg had made a ton of progress on the AMD platform was reassuring to us, and it gave us confidence it was possible. So it's good to see you.
it's amazing to see that we have a model all the way through on it today. It's been a journey.
It takes a village. It takes a village. Bye bye.
All right, thank you.
All right, thank you.
So, we're gonna take a break. 5-minute break. Okay, we only can take 5-minute break.
Yeah. Should be great just to stretch and move around a little bit. side code and actually running it. So,
All right, perfect.
yeah.
Let me share my screen first. Oh, can you guys hear me? Oh, let me. Greg earlier showed a picture next to the cluster. This is, I believe, the picture was MI300, but he and I visited AMD data center in Austin, I believe a few months ago, and this is MI355. This is AMD's latest GPUs. That there is a separate cluster we have on MI355. It's not within the demo, but we're gonna be running on a very similar cluster to this today, for the demo. Just want to show you guys the picture. All right, ML directory. Let's just spin up this. Okay, so basically in the past 2 hours, Greg already have explained how does ScalarLM work in terms of the architecture. That it does have VLLM for inference, Megatron for training, and
You want to zoom in a lot. It's probably kind of hard to see.
Okay. And how it does use Hugging Face for model hop, loading the model, saving the model, and model checkpointing and all that. I guess what we want to cover at this point of the presentation is how can you actually use a ScalarLM and how can you train any model of any given architecture with it. How can you modify different metric or different knobs or different hyperparameters to make the training more efficient. We're gonna, basically everything that Greg has covered, we're just gonna look at the code, how you can modify it, apply it, and run it on both NVIDIA and AMD, and run it also at a scale, whether it is one GPU, whether it is one node with a GPU, or whether it is multi-node with multiple GPU. And we do have one run with 256 GPUs that we're gonna show you the result. But just to start with, there is a part of a ScalarLM called the ML directory. This is the part that, as a user, you can interact with. And by the way, this entire code is open source. You can, I don't know if we have it here. This is the repository. You can get the code, this part of the code is, most of the ML directory, I guess, is going to be integrated inside the actual ScalarLM repository. So at some point, we're going to update it so you can just clone the actual repository. But this is like a fork version of it. And so you can access the code in this repository, but overall, you can train both embedding and language model. The way that we've made a variable in our train.py that you can actually select what type of training you're having, whether it's embedding or language model. The major difference between these two is the loss function. So we have, there is a part of the ML directory I will show you in a minute that it does apply a different loss function depending on whether it is a language model or an embedding model. And we've tried to include special tokens for most of the open source models that are being used very often, including Gemma, Quen, Llama, Range Model, Olmo 3, Mistral, and GPT OSS from OpenAI. It is essentially like how can you add a special token with the input prompt, the system prompt, and the output. Greg explained this part on one of the slides that essentially you can update the gradient based on either the input tokens, based on the output tokens, or based on the entire sequence. It is a choice that you have whether if you set this to be like false, it essentially trains on the entire sequence. So it goes through your entire training point, and it does next token prediction, and it does calculate the loss and the gradient accordingly, and would update the weights for the entire sequence. Sometimes you don't necessarily want to do that. You can actually just get the input prompt as it is, and you only update the gradient and update the model weights and calculate the gradient based on the output. It is possible. I'll show you in a minute like how does the code work, but we've created a variable here that you can turn it on and off easily. And I guess it might be like useful if I show you this for a second. I will go back up. So let's say you're training range model that Ashish just explained how it was pre-trained and post-trained on AMD GPU in US. For this given model, this is the special tokens of when you want to start the prompt. You must add this because this is the model. This is how the model has been pre-trained. This is how the model has been post-trained. So like it needs this special token to actually like knows when a sequence starts, when a sequence ends, when the user is talking, when the model is talking. So this prompt part is what you have as input for your training point. This is where you say, hey, you're a useful language model. You're expected to do X, Y, Z. This is the question. This is the content. All that is your prompt. All of that is your input training point. And what comes out of it is the completion. It is what you expect the model to generate. It is what, it could be your reasoning trace. It could be just simply your response. ScalarLM does give you this option that either upgrade the gradient on this entire sequence or avoid the prompt, avoid the input information, and you only update the gradient on the completion. It is a lot more memory efficient because you don't have to calculate the gradient for like a large amount of like input tokens. So it is a memory efficient like technique that you can apply during training in case you don't have as many GPUs or in case you want to train on one pod or one GPU. This is a very efficient way. And you may wonder, how does that affect performance? How does that affect the convergence of the model over training on a large sequence on a multiple batch size? What we have found is that the difference is not that significant. If you train on the entire sequence, you're essentially penalizing the model on predicting the next token on your input data. It is your choice if you want to do it, but like you have to also like question this: why do you need to penalize the model on next token prediction on the input? If it's really that important, then maybe apply it. What we've noticed is you can get identical performance by just like calculate the gradient on the output. And there was, I think for telelogs, whenever we were training for the network root cause analysis, I think we did try only updating the gradient on the output and updating the gradient on the entire sequence. When we update the gradient on entire sequence, the performance was like 2% better. But the difference is you need like sometimes a lot more GPU, and it's gonna take much longer to train, especially let's say you have a 30,000 context length of 30,000 tokens, and like 28,000 of it is just the input. Like you can avoid all that without like hurting the model as much. I just want to. It is one of my favorite things about like a ScalarLM, that you can easily turn on and off like a feature like this, which is very crucial for efficient training. And we also try to make it very simple for like end users. Like I'll show you where does this gets applied, but eventually like what you need to do, regardless of you're running it on NVIDIA A100, H100, H200, or AMD MI300, MI325, or MI355, it does work on all those GPUs without needing like much of like a change from your side. And this is just another like a parameter we've added that allows you to know how much of the data you want to train on. Usually on the very first one, when you want to test like how the model is being trained, or if your model is converging, you don't need to train on the entire data, especially when you want to do a massive run. for the Open Telco project, we had approximately, I guess, around 300,000 training points for embedding, a couple of million for the LLM, and like around 2 million for the re-ranker. And you don't want to necessarily for the first run let it run on the entire data. So like it's helpful. You just run it on 10% to see how model is performing. Is the loss actually going down? Can you actually run a job? And like for like sanity check, it does really help. And then there are other metrics such as the max training step. The training step in the ScalarLM is very similar to the epoch for transformer library if you have used it before. So depending on how large your sequence is, how many batches you have based on your sequence, how many training points you have, a certain number of steps would be equal to one epoch. And here, one step is, it basically means, I think Greg explained this this is one training step. So like you would have your batch, you would have all the data within like one batch. It goes through the model, the gradient gets calculated, and we update the model. This is called one training step. So essentially you can decide how many times do you want your model to go through the data, and what do you like identify as like overtraining. Like it is like, because essentially whenever you do DDP or FSTP, this data is distributed across multiple GPU. And how many times, and Greg also explained this earlier, that this gets shuffled every time. So like not every data is going to be on the same GPU every single time. It gets continuously shuffled over and over and over. So like how many do you want to, how many steps do you want the model to see your data? This is your choice. But one thing that is really helpful if you save the checkpoints over time, because you might, let's say you put this number at 1,000, and you may realize after 400 steps, the model is not really learning anything. So there is like the training loss is plateauing. It's not going down or going up. So at that point, you can just kill the job and you can load the latest checking point and just save that, and that's going to be your model that you've trained. It does help to usually have a larger max step than lower one, because while the job is running, you can look at the training loss. And if the training loss is not going down or is not going up and is a steady line, you can just kill it. But it's better than not knowing that information. Like if you run it on like 50 training steps and you don't know what potentially could have happened, it is like it's a very useful information to have rather than not having it. And but there is not like a number that we can say use like just 200 or 100. It really depends on the amount of data you have, the context length, the batch size, and the number of GPU you're running it. And it's experimental. Like there is one way for you to do essentially like sensitivity analysis. So you can automatically let a ScalarLM run with different metrics over and over. So like you don't have to do this manual, but I personally love playing around with this because it gives you a lot of insight about your data, your model, what's happening. And the next one is the learning rate, which is obviously one of the most common hyperparameters during training. And depending on how much data you have, depending on the number of parameters you're training, depending on whether you're training an adapter, which is a fraction of the model, or you're training on the entire model weights, 8 billion, 32 billion, the learning rate needs to be different. Especially also learning rate really affects the gradient algorithm. I believe Greg explained this here. That it really affects how you're measuring the gradient, what algorithm you use, and like when you switch from one to another, you may need to justify, modify your learning rate and justify why you're changing it. It is also could be experimental. If you decide that you need more memory and you want to change your gradient algorithm, and I will show you how you can do it in email directory, you probably need to modify the learning rate accordingly. These two are also very important depending on how large your cluster is. It goes back to this slide that Greg explained earlier. It's essentially how large you want this max token to be. Max token is the maximum number of token each training point will see. This is like how much information do you want the model to see in each training step. And then number of the batch size is how many of these chunks of information do you want to be on each GPU. And the way that you identify this number, the way you set this number is by testing. So I think for AMD MI355 there is approximately 250 gigs of RAM available. And whenever you do training, there is primarily 4 things that occupies the memory. It's the model parameter itself, it's the gradient, which is the derivative of the loss over training. It's the activation of the model, and it's also like some of the optimizer states that gets checkpoints over training. So what number you can put for the batch size or what number you can put for the maximum token block size is also very experimental, and it's also like depends on how many GPU you have available. And depends on, are you doing FSDP, are you doing DDP, are you sharding the model, are you sharding the data, are you using NVIDIA GPU with 80 gigs of RAM, or are you using an AMD GPU with 250 gigs of RAM? These two numbers, you gotta play around with it to see at what level you can get more, you can keep basically each GPU busy enough during training. You want to like maximize as much as you can. Like essentially, like let's say you have a GPU, you want all the GPU to be at 100% capacity ideally in the entire training time. So if you don't have much, like if you don't have enough information on the GPU, like you're not using, let's say, 40% of the memory available. And by adding that, you can make it a lot faster. But this two number, again, it's experimental. Like you have to test it. Usually start with a big batch size and a context lens that does make sense for your use case, and check if the code runs. If runs, even better. Then you can do ROCm SMI and you can actually see how much of the GPU is being used, and then try to increase and decrease it until you run out of memory. And that's when you actually decide this is enough, or like this is large enough, or you can decrease or increase it. There is also a couple of parameters in case you want to train an adapter, not the entire model. That's when it gets even more memory efficient. For the Open Telco model or for the OTel family of models that we've trained, and we have open source all the weights, they're all fully parameter trained. So we have trained every single parameter. This is not an adapter. And I guess the main goal that we decided to do it that way was whenever you release the entire parameter, all the layers of weights, it's easier for the user after you to get the model weights and to post-train it further. But like if you only train an adapter, it makes it a little bit more difficult for the next person after you. Like I guess for enterprise use cases, let's say you have to train this model for a company you work for, adapter make a lot more sense because you can have multiple adapters for the same base model. You only need to, you deploy the base model and you can have like 100 adapters that you can inference from. But for the sake of this research that we wanted to enable telecom industry to get this model and then train it on their own data, the private data they have, it just made more sense to do full parameter training. But ScalarLM does allow you to add adapter if you would like, which is a lot more memory efficient. There is R, LoRa alpha, and LoRa dropout. R essentially is like how many, like just to translate it, is the number of parameter you want to train out of the entire model parameter size. Let's say if you have 8 billion, would you like to train 10 million? Would you like to train 100 million out of it? That does allow you to modify that, and that is also like your choice. How large do you want to go? And this is probably one of the most important part of the LoRa. It does allow you can modify it in a ScalarLM directory. Like I'm only showing you where this code can be applied, but like you can modify the code here if you don't like it the way it is. It's called Llama token former inside the ML directory. You can actually modify how you're applying the adapter or how you like checkpointing and all that. But overall, the very important part of it is which layer of a transformer architecture do you want to target during the training? Do you want to only train the MLP layer, or do you want to train both MLP and attention, or do you want to only train the attention layers? And within a given architecture, for every single layer, you have both. For non-reasoning models, for every layer, you have one attention, one MLP. So you can essentially like train all of them, but you need a lot more memory available for the GPU, or you can target only maybe like for mixture of expert, a model like OSS 20B, it has a lot of MLP layers. I don't remember how many expert, is 96?
In which one, sorry?
OSS 20B.
Oh yeah, that's a good question. I don't think it's that many. It's not 128, it might be like 32.
Okay, so like there are 32 expert, there are 32 MLP. For training an OSS 20B model, if you target the MLP layer, you're targeting a lot more parameters. So you need more GPU, and if you don't have more GPU, then you have to decrease your batch size. So like the part that I really want to emphasize is these parameters are very dependent on one another. If you modify one, it's going to affect like the rest of them. So if you do decide to train on the entire MLP layer for an OSS 20B, that's, I don't know, 32 layers. So you have 32 expert for OSS 20B. That's a huge number of parameters. And then if you have that and you don't have enough GPU, then you have to kind of consider maybe decreasing a batch size to make sure you don't run out of memory. And there's also this, which is, as long as wherever you're running this code, if you have enough storage available, it's very recommended to save the checkpoints. It's essentially like saving the model weights at the end of a given training step. Right? By default, right now is 100 for this code, but like depending on how large your model is, and if you have a lot of storage, keep this number around 50 to 100 and let it like keep checkpointing it. It doesn't really affect the performance as much, but it's very helpful to have the intermediate model weights throughout the training. And we also have like a way for you to turn on and off LoRa. Sometimes you just don't want to do adapter and you want to do full parameter training. It requires 10 or 100x more memory depending on the model size. So like training an adapter on a 32 billion parameter versus a full parameter training, it's a huge difference. But you can actually modify that. And then the optimizer, the one that Greg previously talked about, this slide. You can, there's so many optimizer available from the PyTorch library. We can actually read it here. We have attached a link. And which one do you want to use? Why do you want to use that one? It's really your choice, and you can easily modify it here. As long as it's within the PyTorch library and is maintained, you can simply just modify it. I believe Adam W uses the most, uses 4x memory and is faster, but like you can actually use SGD that uses 2x memory and is slightly slower. So you would lose a little bit of like training time, your training time would increase just slightly, but it does allow you to train a larger model on even one single GPU, especially when you have I think with all this memory efficient techniques for training, we were able to train a 32 billion parameter model on one GPU. And like these are the tricks that allows you to do to train a very large model on one single GPU if that's only what you have access to. It does take, maybe it would increase the training time by 10%, but like it's versus not being able to train or waiting 10% longer and actually train. I believe we were able to train almost 32 billion parameter on one MI325, which has around 240, 250 gigs of RAM available. And yeah, there's a huge list. If you're interested, you can review the list and different algorithm for optimizer, and you can modify all those. And you can actually do gradient accumulation steps. This part also, you need to increase this if your batch size is very, very small. Essentially, like, it does allow you to calculate the gradient over a longer sequence that makes the training a little bit more stable. And it is recommended if you're training a very large model on maybe a limited number of GPUs, or like your batch size is very small, you can actually add the gradient step to kind of account for that. It does reduce. It does increase the training time slightly, because you're calculating the gradient across like a longer data points, but it does really help with the convergence of the model if you don't have enough in like a large batch size. Another very common technique is gradient checkpointing, which essentially in a forward pass, when you're calculating like whenever I think it's easier to explain it on this plot. So whenever the batch size goes through the entire model inside the forward, you don't have to save all the activation. You can actually not checkpoint some of the activation at random, that it does save a fair amount of memory. And during the backprop, which is gonna be this step, you would recalculate them. The benefit of it is it's going to be more memory efficient. You can train a larger model on a smaller number of GPU. The downside is it does increase the training time slightly. And correct
Yeah,
me.
it's usually not more than 2x.
Yeah.
You can get a pretty huge memory savings. Like it can be more than 2x memory savings.
Yes. So it is another technique, but it does increase because simply you're not saving all the activations during your forward, and then you have to calculate them during backprop. It just increased the training time, but it is significantly more memory efficient than most of the stuff that we discussed. Also, during one slide, Greg discussed this, which is difference between DDP and FSDP. DDP is data parallelism, distributed data parallelism, that you only shard your data across all of your GPU or all of your node, which is like your batch size. Or you can do FSDP, which is not only the data, but also the tensors are sharded, are like distributed across your entire cluster. If you have one node, it's going to be like divided by the number of GPU available in that node. It's usually 8 for NVIDIA and AMD. On one box, you have 8 GPUs. I think it's around 16 for AWS GPUs. You have like, so like FSTP on one box is going to be 16 bays or like 8 bays. And then you have multiple boxes or multiple nodes. Your model and your data are going to be distributed across like all of them. And that's where like ScalarLM make a huge difference versus any other software that you've seen. Like if you want to only train on one GPU, you can just use Transformer library. You don't need necessarily to learn how to work with another software stack. But the downside is Transformer doesn't work on AMD GPU, for one. For two, you cannot scale up. It is significantly harder for any of the open source library if you want to do multi-node training on like 32 nodes or like 256 GPU. Like this is that's the part that the difference comes in, the major difference. And as you guys know, there are newer self-attention, like a flash attention implementation that it came from. I think the first one was Google DeepMind. Am I wrong?
It's TreeDAO. He was a Stanford student. He's kind of moved around a little bit. He's currently at Together.
Okay. So someone, like there are, I think as of now, we have Flash Attention 3 that is out. But like Flash Attention 3 doesn't work with all the different architectures. So, but like this is another variable that you can modify. Like inside, whenever you load the model with the Transformer library, which is like auto pre-train something, when you load the model, you can, by default, it does not use flash attention 2. I believe by default it uses STQA, unless you like specifically modify to flash attention 2 or 3. It does not use it, but it is more memory efficient. So like it is also another way for you to have a more memory efficient training to use flash attention 2. I did have some trouble with flash attention 3 on some of the architectures and newer one. So I think this is something you can test, but I can guarantee flash attention to work with all the models we have trained for Open Telco project. All the OTel family of models, all of them were flash attention 2.
And that just reminds me, like when you showed me that by default, this is one of the advantages of open source. So Farbod showed me that, and I was really surprised that the Transformers library doesn't just pick the best kernel automatically, because underneath this, you know, it's going to call into some optimized kernel library, and it has like 10,000 kernels, and it's picking good kernels, but it doesn't pick this one for some reason. But you know, with open source software, you know, Farbod found this, and we just kind of looked through every single layer one by one, and it was clear it wasn't picking the right one.
Yeah.
So then you can just fix it.
It is. I really agree with. I think if you just run the code, like you don't specify it. I guess this was an assumption we both had, that we always thought like the model is picking the latest self-attention available for, because each model has a config file, and they usually have that in there, that hey, this model can run a flash attention 2 or 3, but it always by default goes to the basic one. And as I don't know if I mentioned this, but Open Telco models, the primary data we used was text. There was no image. It was not multi-model training. So during the training the model, you can actually blacklist some of the layers. Like we don't have any images, so there is no reason for us to do any training on the vision encoder or like the vision layers. And to our knowledge, these 4 keywords should basically cover most of the model, but it is really encouraged to load the model manually, like locally, and just look at the config file, or just upload the config file from the Hugging Face to see whenever that model was pre-trained or post-trained, the person who did that, what they have called their vision layer. Are they calling it vision model? Are they calling it this vision tower? Is very common. Who picked it? I have no idea. But like, it does help if you load the config file. Just look at what are the different layers name and try to target them, or like blacklist them at this point. But like you can also do it other way around. You can whitelist the layers that you want to train, and but the code as it is blacklisting the layers that you don't want. And this is also very helpful whenever you're running on a large cluster like TensorWave, whenever you have, let's say, 250, 60 to 500 GPU available, by default, all the checkpoints are saved within TensorWave Cloud. And we will gonna show you how it works. We're gonna show you like where these like checkpoints are being saved. But the tricky part is, usually not everyone have access to the cluster. So when you submit a job to the massive cluster like that, it is just a security concern in big companies. Not everyone would have Kubernetes access or SSH access inside the cluster. So one thing that would really help is you save the model checkpoints automatically to Hugging Face, or automatically to a given location of your choice, so your peers, your colleagues, or whoever is working with you can access the model weights live as the training is going on, without you necessarily giving them access to the cluster. Because it's just a good practice. It's easy to download from Hugging Face. So we've added this to allow you to do this. Essentially, like at the end of each, it's kind of related to this number up here, number of like the training checkpoints. Whenever it hits 100, the model checkpoints are being saved inside the TensorWave, inside the cloud, which you have a massive amount of storage. is also being saved automatically on Hugging Face. And it does allow anyone within your org or friend, your research group, to load the model or the checkpoint at the same time as you in case they want to do like intermediate testing of the model. And these two arguably are the very, not the most important, but like it's very important to know what these two numbers mean. Greg gonna show you guys in Kubernetes inside the cloud, inside the TensorWave like cloud. What does it look like? But essentially, each pod, whenever let's say we have one node is one box of GPUs, and there is 8 GPUs in it. Each of those GPUs are one pod in a Kubernetes deployment. So essentially, this is the number that you're telling a ScalarLM. You're telling, hey, inside each pod of a ScalarLM, there is only one GPU available. You're actually telling the software that. And then you're also telling it how many nodes are available. And nodes here means the number of GPUs that you want to run, or the number of pods you want to submit your job to. I think the cluster that we have there is around like 300 GPUs available, but sometimes for testing, you don't need that many GPUs. You may want to use only 4. So longest story short, the way a ScalarLM is designed as of now, keep this number always at 1, because this is the number of GPUs available in a given pod. This is always 1. But you can scale up. You can use multiple pods during the training. Essentially, if you put this number 2, that means your model is being sharded across 2 pods or 2 GPUs. If you put this model 256, it's going to be sharding the model, the weights across 256 GPU. So that's basically how you scale up or scale down during your training. And we thought it's going to be helpful for us to put this together. This is you can use the chat format of the Hugging Face library, and that is essentially does the same thing. It does add the system prompt, a special token to your training point. But what we liked about this is we wanted to have full control how we are adding it. And if you use the chat template of the Hugging Face library, sometimes it does add like extra special token, or sometimes a system prompt that if you don't need it, if you don't want it, you can easily avoid it. So like we have a very simple function that regardless of what model you're using, whether it's OSS, Mistral, Olmo, Range, Gemma, Llama, Quen, it does add the special token for you. And this is open source, by the way. You can just get it and add more models to it. There's also a tricky part. Some models, including OSS 20B, depending on whether you're training it with reasoning trace or without reasoning trace, their prompt is different. This is how OpenAI have trained their model, and you have to like follow what they have done. If you look at it, it says like this is their system prompt. I really did try to remove it. I couldn't. Like they really force you to add this to during your training. You can't remove it, and it says your ChatGPT, a large language model trained by OpenAI. It doesn't make sense to me, because like you're gonna lose like 20 tokens in each training points, and when you scale up, this is like maybe you're losing 10% of the memory for.
Yeah, it makes me wonder if how serious they were about open source when they do stuff like this, because the way you usually control for this is you train it with and without, so that the model becomes robust to whether it's there or whether it's not there. But when they did something like this, they probably trained it only with that, and so it's not robust. So why would you ever do that? Maybe you were rushing, or you just didn't bother to do it.
It was pretty annoying, because I guess we tried many ways to try to remove it. It just didn't work. And by the way, this knowledge cutoff, or I guess this one gets added, but here's the tricky part. You can basically, they want you to have low, medium, high reasoning, and it just means how long is your reasoning trace sequence. For what we did for Open Telco, our reasoning trace was, I don't know, somewhere between 100 to 400 tokens. So that was low reasoning. And that's why like you see low here. But this is a variable. You can modify to medium or high, but you probably need like provide a little bit more reasoning trace. And the other part that is also different is whether you're doing instruction tuning on top of OSS or you're doing with reasoning trace. Just the prompt is slightly different. That's why we have like two different variables here. Then you just, this is basically how you format the data. I believe Greg already explained this input and output. It's essentially like this part that he was explaining earlier. What is the input? What is the output? Do you want to update the gradient on the output or the entire sequence? That's how like, you don't really need to modify anything here. It's already like a variable. The only part that I think is going to affect a training job is, as of now, the code assumes that your training point, the input prompt is called prompt, and the output of the model is called completion, and your reasoning trace is called reasoning. If you don't call your training points, if you don't create a training point with these fields, so perhaps you probably just need to modify it. But in order to make it very clear, we have added sample training points here for you, so you can actually see what we call prompt, what are we calling like a reasoning trace or the completion, and it's just like there for you to compare. And if you have your data in a different format, you just need to modify this part of the code. Like not this part, to be honest, just these 3 lines needs to be changed. And then the rest is a lot of like, you create a local config for an ML directory, you submit a job, and I guess let me just briefly cover this. I don't think we're gonna have enough time to go over every single detail of ML directory, but this is, the ML directory, sky is the limit. Anything that is related to data science and is not much related to the infrastructure part, you can modify in here. Like for instance, in the Llama token former code, this is where we are actually adding the adapter to the model. As of now, there are 2 ways that you can add an adapter to your language model with ScalarLM. One is LoRa, one is token former. Both of them are implemented already. I think with token former is much newer compared to LoRa, and sometimes it's very sensitive to the layer names. So like with LoRa, it's a little bit easier to configure it in my experience. With token former, you have to like, again, load the model config file, look at the layers name and try to target something, but both of them are just an adapter, like a fraction of the parameters are being trained. And you can modify it if you have, let's say there is another way of training an adapter and someone open source a code, you can modify it here. And I guess the other part is, this is also very important, it's called the load token former model. And there is this part of the code that is very, very, like, it goes through the training and it does apply an adapter. It does, like, for instance, in the materialized model, let me show you this part. Okay, here. So, as you can see, like, this is where we apply the different attention implementation, whether it is self-attention 2 or 3 or the basic one. That's where it gets applied. This is where we actually apply the full parameter training. If you set full parameter training to true, it would skip adding the adapter. Like, or if it's false, you're actually going to train on the entire model parameter. So you're not going to do any sort of like full training. You can apply the gradient checkpointing. This is where the code is. this is where we are actually blacklisting some layers. If you don't like skipping some layers and instead you like to train on certain layers, like you like to be whitelisting, then this is the code, part of the code that needs to be modified. And let me look at what else. Oh, the training loop. I think we have one slide about what we'd like to add to this, especially the training loop code. This is where, let me show you for the, okay, here. As of now, for training an embedding model, we are using contrastive loss. Essentially, you have sentence 1, sentence 2, and how different they are. But like some of the model, embedding model we have trained, we use MNRL. It is multi-negative ranking loss. And it is a simple modification that needs to be changed here. That part of the code has not been pushed yet, but overall, if you look at sentence transformer library, there is so many different loss functions you can add here. And essentially, this is the part of the code that you need to modify to go from one loss function to another. And I think we do plan to make it a little bit easier to go from, for instance, one loss function to another. I think that's part of the code that's probably gonna be changed in the next few weeks, and the change is gonna be pushed. So as long as you clone the recent ML directory, you're gonna have that code. And yeah, I think should we go to the?
Yeah, let's try running it.
Let me. I think next is the Kubernetes deployment, and if you want to give them like a like an overview, how does?
Yeah, sure. Do you want me to?
Yeah,
it might be easier to actually. Do you have it like logged in over there somewhere?
Let me log in really quick. I'm inside the control node right now.
Okay, awesome. So I'm just gonna try and make it super big so it's easy to see. Hopefully that's super big. Okay, so this is the TensorWave, as you can see there, MI325 cluster. This one has, I think, 256 GPUs. So we're gonna use Kubernetes. Kubernetes is a way to kind of schedule pods or schedule containers on all of the different GPUs. So ScalarLM, kind of Farbod was just showing you some of the source code of how you edit the model. As you can see, it's all Python. It's all basically PyTorch, Hugging Face. You can change whatever you want in it, but then you build it. So you clone the repo, you build it, you get a pod, you get a container. And we're going to deploy some of the containers. So Kubernetes is all about, the Kubernetes command line. I don't even know how to say this thing. Sometimes people call it kubectl or kubectl or kube control, or I have no idea. But anyways, I can get the nodes. So this thing has, I don't really want to count all of them, but each one of these is 8 GPU. Giant GPU node, like we showed in the picture. So they're all been joined together into a Kubernetes cluster. We can kind of look at what's running. I'm just going to look at one that's already on there, and then I guess we can kind of go through starting one. But let's look at an existing namespace. So I had one with 256 GPUs. So I can get the pods. And pods are like a container, or in ScalarLM land, this is going to be controlling one GPU. So each one, you're going to get 8 of these pods on one node, and then all the nodes are together into a big cluster. So here we got, kind of see, we're 256 Megatron workers. So there are 256 instances of ScalarLM, and then each one is bound to a GPU. So collectively, this thing is like the cluster. You kind of notice there's there's 4 kind of pods in ScalarLM when we did this deployment. So one is this one, which is what we call the API. That's how you like connect to the ScalarLM cluster. You kind of think of ScalarLM as one big machine. It's not a lot of little things. It's one big machine, and the interface to the big machine is this API. There's Cloudflare here, which lets us connect to this thing over the internet, and you might actually even be able to do this on the, you know, I don't know if I could go to like a web browser. Could just do this maybe. I could go to, I think it's called, or no, it's called TensorWave API ScalarLM.com chat. Probably misspell it.
If you send it on the Slack, I can just click on it.
There we go. Hopefully the internet works. There we go. Chatting. Okay. So we got, it's running the Essential AI Range 1. So let's say like, who are you? Right, developed by Essential AI. Please don't destroy this API, you know. It is public for the demo. But you also notice down here we have one VLLM worker in this cluster. It's kind of intended to be a training cluster. So you could very easily hug this thing to death, you know. But okay, so let me also just show. So those are the pods. I can also exec into the pods. So let's just do Megatron 0. Megatron 0. Exec. Run a shell in it. Okay. So now I'm inside one of the pods. We install a Slurm overlay that's inside of Kubernetes because we're going to be scheduling our jobs with Slurm. So I can just, you know, run sinfo, which is I'm going to get the status of the Slurm cluster. So you can see I got 32 GPUs that are allocated, and then I guess 225 or 224 that are idle. And I can look at the queue. And there's a job that's running on 32 GPUs. And I can kind of go, there's a jobs directory with a bunch of models in it. I can go into this model. And so the data that the model is being trained on is in here. The ML directory, which is all of your training code. So you wrote custom training code. You want to modify one line, submit a new job, go right ahead. You know, every training job gets a separate copy of all the training code. So you can modify it whenever you want, but it's still running in a container, so all your dependencies are locked down. And then we got a log. So you can just look at the log. And when you launch these jobs on a lot of GPUs, the logs get kind of verbose because it prints out like every single time. But yeah, so I was just running this one previously, and I just wanted to show like an example of a job that's running. You know, this one is I don't know what, it's just training. It's just an example, but doing 32 GPU training. So let's see, I feel like it might be helpful just to kind of go through like the process of setting one of these things up. Because this is one that's already set up, but like what does it look like to tear down the cluster, to turn it on? Like you have a Kubernetes cluster, how would you actually install this?
Do you want to do it on the FSCP test? That one only has like much smaller, so it's not going to take like minutes.
Yeah, exactly.
Yeah.
I feel like you should. Do you want me to do it or you want to do it?
You can do it.
Okay, let's do it. All right, I'm going to exit out of that one.
I think it's inside. Do you want to show them the Helm charts?
Yeah.
So it's inside Farbod ScalarLM.
It's this thing, right? Get pods. Okay, so let's go Farbod
ScalarLM with capital S.
Got a little lag, SSHing all the way across the world.
Deployment. Yeah.
So in here, okay, so this is just, if you cloned ScalarLM, you get this repo. Okay, so inside deployment, we're gonna do these deployments with Helm. You know, you can use whatever you want to do Kubernetes deployments, but we like Helm charts because it's kind of software as code or infrastructure as code. You can version control your deployments. Which one is it again?
It's the FSTP test. It's only 2 GPUs.
Okay, so I'm gonna look at Helm, and see what's installed. It's in a namespace called FSDP test. And yeah, there's a deployment called ScalarLM. So I'm just gonna uninstall it. Uninstall ScalarLM. Okay, so uninstalled, and then we can look at the chart.
Oh, it might be also interesting for them to see when it's getting terminated.
Oh, sure.
Just the Kubernetes command. But I guess it might be too late by now.
Yeah.
Might be already down.
No,
oh no,
still
that's interesting.
going. Yeah, so it's typical to use like watch on the CLI just to say like, okay, we can just look at the status as its Helm is tearing down the deployment. One of the nice things about this is you can have a lot of different deployments, so it's very common to have like this deployment for this user, or this deployment for this team, or this other deployment for this other model. You know, I want to switch models, so I might have like 10 models simultaneously. I've seen production teams will have like 40 deployments, you know, on a big cluster for different reasons. But Helm makes it pretty easy to kind of like install, uninstall. So we can look at values is kind of like the Helm config file. So you may want to adjust what's going on with this. So we have, you know, these at the top, like which ScalarLM image. You know, you could build your own image, or you can use one of the pre-provided images. These are, you know, this one's built for AMD. And then I guess this is running Qwen 3.
Yeah, and please don't use my tunnel token for Cloudflare.
Yeah, well, you can rotate your token after the talk.
Yes.
It's one button. It's a demo. It's not a production environment. You know, this is a test environment.
Should we show them the Cloudflare?
Yeah, let's do it eventually. So I really like Cloudflare tunnels if you've never seen this before, but like it's a way of, in this cluster, you know, who knows where it is. If you went to the website, you could actually connect to this cluster right now, you know, from Barcelona. But normally it's annoying to set up, you know, connections and like getting into a cluster like this. We really like Cloudflare because it kind of brings the whole internet like straight into just your deployment, and then it can't get out. It's all encrypted all the way through. It can't get out of your deployment. So we really love this thing. But anyways, what is the other stuff that's going on here? Like we picked a model. You can change your model. You can pick what D type it's in, how many GPUs are being used for training, how many GPUs are being used for inference. This GPU memory utilization, if you're a VLLM user, you can be familiar with this. This is just like how much space on the GPU is VLLM taking up, and it's both the model and all the caches that VLLM has. But yeah, okay, so let's just go and redeploy it. So let's do Helm into the same name. Oh, actually, I want to do the whole thing. So I'm going to make a new namespace, which can be our, I don't know, demo. Create namespace demo.
Do you want to create a new folder for it?
Yeah, so it's typical to have one chart. This is a best practice that we have, like a namespace, and then one chart for it because you don't want to like mix them up. So I'm just gonna copy this one into demo, and then we can deploy it. I'm gonna go inside of it. It has this ScalarLM directory. I'm gonna do Helm, demo namespace, install, ScalarLM. This is a deployment named ScalarLM, and then I'm going to deploy it using the chart in the ScalarLM directory. So there's that. And it'll take a minute. So it's deployed. And then we can monitor it. Okay, so depending on whether or not the worker nodes already have the containers, it'll do this container creating. This means it doesn't already have it, so it has to kind of download it from wherever it's pulling the images.
You can actually describe the pod so they can see it when it's downloading it.
Yeah, sure. Very fair. I like this one because it has a stable name.
Yeah. I think if we...
So it's scheduled. Attach the volume. Did I? Oh yeah, oh, they are running already. There we go.
All right, perfect.
So, yeah, we can try logging into it. Actually, I feel like I might want to do one of the Megatron ones. It's just more interesting.
Oh, I think no watch, I guess.
I really shouldn't have put watch on there. It's a typo. Probably hung this thing. Yeah. I feel like I'm gonna need a new terminal, sorry. Oh no, wait, it's just ridiculously slow all the way across the world.
Yeah.
Sorry. Q. Is it possible to do a new terminal? I feel like I hosed that one.
Let me, one... It's not going out at all?
It'll work eventually. We're just all the way around the world, so the latency is super high, and it's going to take like a minute to resolve it. Q.
I guess we can open a new one.
Yeah. All right. Okay. So back in here, this one only has 2 GPUs, but Slurm comes up. We can try submitting a training job to this thing. Or we could try inference.
Oh, I think might be some challenge. You're using the same Cloudflare tunnel token on 2 deployment now.
Ah, you're right.
I think...
so we should do Cloudflare.
Yes, I think if you want to do like a live, then let's log into the Cloudflare really quick and create a new token.
Sure, let's do it. So that was the demo.
Yeah.
So let's do... How is it there? Demo. Uninstall. So yeah, one of the things you'll notice about the workflow of this is like you do a deployment and then you realize, oh wait, I want to change something. I want to change the Cloudflare tunnel. You just uninstall, reinstall. It's pretty fast.
Yeah.
So yeah, we'll get to see what it's like to create a Cloudflare tunnel. I feel like, you know, if you're not already using these things, you should be using it.
Yeah. Let me, I guess the part that, essentially we just want to modify this to create a new way for this deployment to talk to outside of the cluster. And it's very straightforward. Once you have a Cloudflare account, there is a section called like connector, and you can just create a new tunnel with a new API. You can see that there is a multiple deployment we have here. This FSTP is the one that it's already deployed. I guess let's just create a new one, call it demo.
Yeah, so what this is doing is, anyone on the internet can connect to Cloudflare. Cloudflare has a network that's like a global set of POPs, which are like ways of connecting or data centers to connect to, and then they forward everything within their network. And so there's like a connection from your browser into it, and then this is making a connection from their network into this deployment.
The URL is a ScalarLM 8000, right?
Yeah.
ScalarLM 8000. Okay.
Yeah, so this is just local. Once you get into the pod, it's going to forward to the ScalarLM API, which is a web server on port 8000. But it's you don't have to encrypt all of your stuff yourself. The connection that's going into your pod is encrypted by Cloudflare.
Here, this is the new token for you.
All right, let's copy it into our chart. A little lag. It's okay. A little bit of lag. Okay. So then we can install again.
It's also very interesting. The pod right now is turning on, like we're installing it. As you can see here, the demo is inactive. And as you refresh this, when the deployment is up, it's gonna say either healthy or down. It's already healthy, so it's up. I guess we call it demo.
Yep.
Yeah.
Okay.
So it's up, and not all both GPUs, but like one of them is up. So the Cloudflare has actually is right now connected to this deployment.
Yeah, and at this point, running Slurm on Kubernetes is kind of they were not designed to interoperate together, but at this point, it's pretty robust. Like we have a lot of auto detection and auto scaling in Slurm. So if you like resize the underlying cluster underneath it, just like is happening here, the pods are rescheduling. They kind of automatically reconfigure Slurm so that it's aware of them. This is also pretty helpful for fault tolerance because in these clusters you can have like pods falling out if the node underneath it dies, and Kubernetes can just migrate it immediately over to another GPU, and then the pods will come back up and then they'll rejoin Slurm. So you don't really, it really helps with a lot of the fault tolerance things that you do not have on bare metal. Okay, so let's launch a training job, or maybe we can just try the API, right? What?
Yeah,
sorry,
there is.
It's not my laptop, right? Where do you usually put this stuff?
Let me just add one thing. So this is usually what I do whenever I make a new deployment. You actually want to make sure like the Slurm is working, and the pods are recognizing one another, so they can actually talk to one another. Usually what you need to do is essentially go inside one of the, this is all the names, go either inside one of the GPU pod or the VLLM pod. Like let's just go inside this GPU one. Greg has already showed this, but it's kind of important to go here and you do sinfo. What happened? Oh.
Sorry. There's probably a little debounce
Okay.
lag. It's okay.
So
it's all the way around the world.
Yeah, every time I personally make a deployment, I run this command to make sure like the GPU can see each other. You can actually see if there is any very slow. You can actually see if there is any job being submitted, which is there is no job at the moment, and then this is I personally just train it this way.
Okay.
I'll
Yeah, do you want to launch it?
yeah, let me get the link. Just show it to them in the other one. So we're calling this demo, right?
Yeah.
Okay. I guess let's submit a job. The job has been submitted. Now you can actually look at the logs.
Yeah, so what you showed there was the, you launched it from a Python script that just pointed at the cluster. You can have as many clusters as you want, just point to different clusters. This is a script running on this laptop. So we submitted a job from this laptop to a cluster on the other side of the earth. And there's also the ScalarLM command line, right? So there's like a little CLI where you can say, oh, just look at the logs. It's kind of whatever gets printed out by your code. So the ML directory is all whatever your model code is, and it's basically any Python or Hugging Face or PyTorch code. And yeah, so that's like the model that got printed out in PyTorch. I don't know, how many, is this a multi-GPU job or a single GPU job?
I think it's on 2 GPU.
Okay.
Let me check. Yes, we are running it on 2 GPU.
Yeah, and this cluster only had 2. This deployment only had 2.
We're doing FSTP with gradient checkpointing. We have 4 gradient accumulation step. We are using AtomW for, and it's an adapter actually. So this is not full parameter. And we are using AtomW as a, the gradient algorithm for a gradient calculation. And yeah, that's basically the setup. And then there's also an interesting part. You can actually go on the other side. Inside each pod, there's going to be a jobs directory. And if you look at it, so far in this deployment, we have only submitted 1 job. So you only see 1 folder. But as you continuously submit more jobs, more folder gets created here. And you can actually go inside the given folder, which is the same ID that gets automatically generated. And you would have what data you've submitted, what is a config file. Let's just look at the config for a second. So this config says this is a database hash. It's on the batch size is 2. This is the learning rate. This is the model name, number of steps you're training. This is the block size. We are training it on 2 GPU, and we are training it for we are saving the gradient checkpoint every 100 steps. You can actually look at the data itself. So you can do. This is the data that was submitted to this training job. Like the data automatically gets saved on TensorWave, and like you can actually look at it per training job, and it's easy. It's a lot easier to keep track of it, and then. Once the job is over, there's going to be a checkpoint right here that you will be able to actually load it, save it, and it would get, I don't think we are saving it right now. I don't think we are saving it as we speak.
You mean to Hugging Face?
Yes, I think it's false, but if it's not false, it would get saved to the Hugging Face. And let me see what else I can show here. Oh, and there's an interesting part. Here and there, you may have trouble. Essentially, like maybe their job is not running, the code is not working, you get an error. There's a couple of useful commands I was just maybe describe and logs.
I think that's a great idea.
So let's say demo get pods. So we have right now 2 GPU node, sorry, 2 GPU pod and 1 VLLM pod. Let's say the training is not working for any given reason, and you want to actually look at the logs. one way to do it is basically you can describe the pod to see if there is any issue with the pod itself. Oh, you gotta describe pod. We can actually see the container has been created and the container has started. So in terms of like describe, you're good. That basically means the pod is healthy and is working. So if anything has failed, there's another way to look at it, which is you look at the logs of that given pod.
Yeah, so in there, that was Kubernetes scheduling it. It can fail to schedule for all sorts of reasons, like you ran out of GPUs, or you ran out of ports, or the image failed to pull, failed to connect. There's all sorts of reasons why it can potentially fail.
Yeah. And then when you look at the, this is the GPU pod, we look at the logs. There's also another way that we can essentially go inside one of this, and there is a Slurm directory, which is...
Yeah, so previously we were looking at the Kubernetes logs, but you can also go inside of it and look at the Slurm overlay and look at all the Slurm logs. So Slurm has its own logging and debugging system.
You can read the logs there's 2 log files for a Slurm to see actually what's going on, like how it's being loaded, if there is any error message. There is also another full file, which is this one. You can, one thing we are planning to add that might really help is, instead of logging into the cluster, instead of going through each pod, looking at the Slurm logs, looking at the Kubernetes logs, or describe it, we're wanting, I think it might be really helpful if like an LLM does this part for you. So as soon as you want to look at the logs, like you run one command and it does all of these intermediate commands for you and send the logs automatically to an LLM. Because essentially, this is a small job, this is a tiny deployment, but if you have a lot of different GPU, you're gonna read 3,000 line of logs to see where it's going off. And that part, LLM are actually good at it. Like, it's just reading it and telling you where to look.
Yeah,
yes.
That's very much what the workflow is like. It's like, okay, there's something going wrong, 50 pages of logs, paste the entire thing into Claude, it can read faster than me.
Yes. So it is not for solving the problem, like it's not like you solve all of your problem, but it does read the logs faster than you do. So like it can tell you, hey, pod number 1 or GPU pod number 2, this is the error message, this is where you need to look, and that kind of reduces the intermediate steps before you figure out where to look. And it doesn't always say that is the solution, by the way. It's not like, might be multiple location, but it does help. But right now it's working, but it has happened in the past that it just didn't work.
Typically when you're doing, you're moving to a new model, you're moving, ScalarLM has a lot of like library dependencies, you upgrade some of the dependencies, you move to like a new cluster to deploy on. There's a lot of things you have to set up that don't just work automatically. Like, a common thing in Kubernetes is like the file system, like getting all your, volumes and everything mounted and everything allocated. And, in the bring up process, you really need to rely on this stuff to see what's happening and to kind of have a debugging workflow. Also, when you're doing one of these big training jobs, like, like the Essential guys were saying, like, your loss spikes or you get a NAN or something. It's like, you need to go back and figure out exactly where that's coming from. Or if you're doing a long run, one of the bots, goes out, and then we do have logic in ScalarLM to kind of like detect that stuff and try and retry. Like the job will auto requeue. Kubernetes will try and fill back in all the workers, but you wake up and then there's a bunch of logs and a bunch of things have crashed. You want to be able to go and look it through and figure out what happened.
I think it might be helpful if I show you, like, one more thing that I guess we can show is, right now, even though we have one deployment that just submit a job that is working, in parallel, you can submit another job to another deployment. Have we messed up the previous deployment because you
I
make?
did uninstall it. You may need to have to reinstall it. If you reinstall it, I think it should be fine just from the same chart. That's exactly why it's good not to delete the old charts.
Yeah. Okay. All right. This is the previous deployment that Greg installed. We're just installing again just to show you that when you use clouds like TensorWave, you essentially can have multiple deployment all at the same time. You can train on all of them. You can inference from all of them in parallel. They don't. It's a benefit of Kubernetes. They don't interfere with one another. So even though that previous job is running, we just made a new deployment. And as I mentioned, let's just make sure the SLRM is actually working. So like we go inside it again one more time. It does actually work. So there's 3 pod, 2 GPU node and 1 VLLM node. So now that is working, let's go and submit a job to it. I think it's just the name is slightly different. Instead of demo, we are calling this FSDP test. So let's just show this really quick. So we're just changing the ScalarLM API URL, and let's just do it for. Let's say we do 20 steps on a slightly different max token. We submitted a job to a completely different deployment. This is not the previous one. And then let's look at how it's going. Is it helpful if we walk you through the logs for a training job? There's like 100 line of.
Yeah, I feel like it might actually be good to be like just pause and just say like, what do you guys want to see? You know. Any thoughts?
Any question? I think my something that I really like about.
You may have to like raise your hand if you want to talk.
Do you have a question? Oh, hold on.
Yeah, we need to do the mic.
Where is the mic? I can't hear you.
Oh, there it is.
One thing I've noticed, I feel like because we are in Spain, the cluster is in US.
Yeah, of course there's going to be latency by going all the way around the world.
It's like we are sending data like across the continent.
Yeah. It's going under those
I've never
undersea cables.
I've never done this before. I feel like I'm the farthest away I've ever been from the cluster.
Okay.
This is a multi-continental training.
Not in space, you know.
This is interesting. Sorry.
Hey, no.
Hold on. I can't hear you. Oh.
Thanks. There's a whole sea of questions that I would like to ask, but due to physiological limitations, I will just ask one. Do you have to change the infrastructure parameters, configurations, depending on the model that you would like to run? Like, I don't know, there might be some networking or scheduling configurations that could aim or help some application or some even model, I don't know, and maybe with Kubernetes you can make groups of pods that can perform better operations together.
Yeah, absolutely. You have to think about the model that you're deploying when you're setting up the deployment. We have a little bit of like rules of thumb of right sizing of like how many GPUs of a particular type do you need for inference, how many do you need for training, and then so the first thing is like, will it even fit? You know, do you have enough memory to even fit the model? You know, these models that we're doing here are kind of like on the small size, but if you're doing the 400, billion parameter, giant MOE, you have to get a lot more resources. So that's the first thing, and then probably the second thing is like, do you have enough GPUs to train on all the data, as you're trying to like really scale up and train on a lot of data. So those are probably the two biggest things, but then also the model architecture itself. I don't think we're really going to show it here. We have time to show it, but the way you apply the collectives or the distribution strategies like DDP or FSDP is not the same way that you do it for every model. Like it kind of depends, and there's no system that automatically does that for you. You kind of have to think about it and say, oh, I'm going to apply it to this layer, but not this layer. Kind of like what you're seeing with Farbod, like he was showing you adapters, but it's the same kind of thing with distribution strategies.
I was also thinking. I think not in terms of like a different model, but if you go a different GPU series, or you go from NVIDIA to AMD, there is or if you go from one cloud to another, there are features inside your charts for the deployment that needs to be modified. I feel like
it's definitely worth looking at some of the more detailed charts. We were just looking at the config file for the chart, but then we can look at the charts themselves.
I think just I'm from the user perspective. Like at AT&T, I don't spend time on developing these features. This is done by TensorWave. This is done by AMD. This is by AMD Silo team on the AMD GPU side, and similar for NVIDIA is being done by NVIDIA. But let's say you go from MI300 to MI325, or from MI325 to MI355, the latest AMD GPU. These features here are how your network communicates, and Greg can explain more in detail in a minute. But like, usually the way that we have been interacting, for instance, with the AMD team, the AMD Silo team or like a TensorWave team, they would like let us know what are the better features to turn on here. And there's also like a AMD network or NVIDIA network operator that is supposed to pick up some of the features automatically, but eventually this needs to be changed from one chips to another. So NVIDIA features are going to be different from AMD, and within the same GPU family, if you go from one series to another, this is going to change. Do you want to explain like high level
so
what they
this
do?
stuff is setting up the high performance network. So not all clouds have this. You go to, like a standard node on a standard cloud is not going to have a high performance network, but if you get a training cluster, like this is a training cluster, it's, I think these are 8 400 gig links on every single training node. And so if you just try and send regular network traffic over those things, it doesn't really work. You have to use these like specialized low-level transport layers. And so when you're doing that, you have to kind of wire all of that network stack all the way from the node and the network card and the network drivers, like all the way up into MPI and into Slurm. This is why we have Slurm, because setting up all of this stuff is like 10 different layers, and it's a lot of really low-level, complicated OS driver software. So I'm not going to talk too much about it, because this kind of thing could take like years to talk about, but I think configuring the GPUs, configuring the network, configuring the storage, Kubernetes is all about resources. There's also another important thing on these things is just like making sure all the pods can talk to each other, like configuring like DNS and like the regular network. So yeah, there's a lot of settings, and the point of these frameworks like Helm is just to try and abstract this away. But realistically, like different clouds, different machines, different environments have different settings. And so if you're moving from one to the other, if someone already did it for you like this, you just install and go. But if you're doing it, you may have to be in there and editing a bunch of these values. And, I wouldn't say this takes an enormous amount of time, but
Yeah. Oh, quick random question. Are you still letting that training job on the 200 GPUs run?
yeah, I was just in case we wanted to look at it.
It's still running, right?
Yeah.
I feel like that you might have causing us some latency.
Oh, sorry. Okay. I don't know.
That's 200 GPU.
Yeah.
Okay, and then this is like all the Helm chart that you can modify. And I personally rely on TensorWave and AMD like to tell me as like for AT&T as a user, what do I need to put in this Helm chart? Like I think I've done experiments on like before and after adding one feature, whether it's gonna help with like FSTP or is it gonna like the NV link that Greg just described. It's like whenever you shard your model across 8 GPU versus across 16 GPUs, during the all reduce step, which is I think Greg covered it in here. During the all reduce, these GPUs needs to communicate with one another. He's gonna say, hey, I have 10% of the model weights. This is the gradient that I have. This is the average of the, this is the gradient I've calculated. This is the GPU, second GPU says this is a gradient I've calculated. And then all over like your entire node, they all talk to one another. And then you average all those. This is just like a high level, very simple way to look at it. But then this network needs to communicate. And the network speed has a lot to do with these features here. The one that we just showed, this one.
Yeah, this is the difference between your step times are about the same time as they were on a single GPU versus they're like 10 times longer, 100 times longer. You need these high performance networks if you're going to train. You don't need it for inference, but you need it for training.
Perfect. And one other question, very quickly because my bladder is about to bloat. So,
Physical limits.
as a user, what is your training workflow for an LLM? I would imagine that it's optimized for one GPU, then scale up to many GPUs, and then try to optimize the performance of the results. But I don't know if it's...
I guess before we run out of time, that's a very good question. We have a few slides left that actually would talk about that. I think this is a very good one Greg already covered, that you go from 1 GPU to 256 GPU. Let me maximize this screen.
Yeah, you want to make sure that the one GPU is well tuned before you try scaling up, because there's usually a lot to do even on a single GPU.
I think once you have enough evidence that on one GPU you're having good memory efficient, like your training job actually works. Before going too crazy, maybe train on one node. One node means you don't have between node communication. Like you want to make sure like the SLM works within one node with 8 pods, for instance. And then when that works, then you increase it to 2 nodes, 3 nodes. And sometimes I think once it happens, like once in a while, just one of the nodes just turns off. 1 minute. We have 1 minute, I think. Okay, let me show you just the model. This is all the models we trained on TensorWave cluster with AMD GPUs. And we also trained, we've tried the code on both NVIDIA and AMD GPU. And just to give you like a high level, I think we trained 17 language model, 10 embedding model to rear anchor. All the models are open source. All the weights are Hugging Face. The data we use is open source. The code that we use to train this model is open source. So like, assuming you get some GPU from TensorWave, you can run the same code on the same data, train the same model yourself. So like, you don't really need us like.
You can refer back to the recording of all of this if you're curious about any particular section.
That's true. So you need some AMD GPU or NVIDIA GPU to run this. So like, I'm assuming like if you actually want to run it, you need some cloud or a physical GPU in your local environment. But this is all the language model across for abstention training. Abstention basically means the model refused to answer to your question if does not have enough content. So let's say you're providing content that has nothing to do with the input question. After the training, we realized that a tiny model does better than even Claude and GPT 5.2, simply because these models are generative and they would want to talk, they would want to generate something. Then we have the embedding models. Yeah, sure. And then we have the embedding model, and you can actually, this is abstention, this is the correctness, and last but not least, this is 10 embedding model, which is retrieval. Essentially what we are showing here with a 300 million parameter embedding model, like the Gemma from Google DeepMind family, if you fine tune it, you can outperform one of the largest embedding closed source model from OpenAI called Text3. And they're kicking us out. It was, we gotta wrap it up. All good?
Okay. Appreciate everyone
right.
who stayed to the end.
Thank you.